the devices, you must be aware about whenever you put the command show VLAN brief, you would be seeing FDDI, token ring, and all of these uh, interfaces or all of these VLAN being present over there. Okay. Apologies for that. Uh, and majorly our focus today, or everyone's focus today, would be on to learn more about Ethernet. Uh, Again, Ethernet is an IEEE standard, and majorly the switches or the bridges are the devices which are working on Ethernet. Now, bridges are, you can say, old systems which are obsolete, whereas Ethernets or the switches we are still using, and everyone is aware about that. If we move ahead, the first question is, how does Ethernet works? So, in the shared environment, Ethernet used to have this basic concept, or if we talk in past, in traditional or hub-based environment, which was also an Ethernet port environment, only one NIC could successfully send a frame at all point of time. Um, so in simple words, in a hub, one guy can send a frame, rest of the guys would simultaneously listen about that information on the wire. Before an Ethernet NIC would put a frame on the wire, it would sense whether the wire is already occupied or it is not occupied. Even after doing this, there used to be collision which used to occur. If if it was like, let's say, copper, then we would use it with the help of voltage level. Now, this sensing process, because Ethernet have a multiple mediums, the NIC card would eventually transmit the frame, and uh, when it would be received on the destination side, it would be received by all of the guys because everyone was sensing it. This used to be the logic with traditional hub-based environment. Now, what exactly this is where the CSMA part of the whole concept used to work, which is a moment, my pen is giving me some problem. It should be good now. Not sure what is the problem. Yeah, now it is good. Yeah, so this was the major concept which was being used at Courier Sense Multiple Access, which is nothing but CSMA, which is a part of your Ethernet, which is using the concept. Now, how does collision detection would occur, which is your next part, which is CD, is Ethernet based technology that they try to sense the wire. When they try to sense the wire, what they do is, let's assume they try to send a frame, and or try to sense the voltage, and if no one is consuming anything, so what they would do, they would put their frames on the wires at same point of time, because at same point of time there was no option, no one was using it, the status was all clear, and when it would land on the layer 2 technology or Ethernet based technology devices, they used to collide. Now, in such case, whenever a collision will occur, the two frames which are colliding with each others, um, what again will be done once they are collided? They will have to resend the frame. In such instance, every NIC card, which is this NIC card here as well as this NIC card here, will send a jam signal. So this jam signal is nothing but a special signal whenever a collision is occurred, that for a small period of time, small random period of time, they will wait and they will not send any data before this wait period is over. This is the jam signal which is used for a random period of time where the two machines will not send any kind of data, and again they will start sensing the wire. This concept is implemented with the help of collision detection. This whole concept is how the collision has been detected and it is avoided. Now, because Ethernet experiences a collisions, network devices, those are having a same medium, uh, are said to be part of same collision domain. Clear? I guess you guys cannot unmute yourself, so I will assume that it is clear. But these are some basic concepts which you may have learned way past into CCNA if you guys are quite old into the networks as a part, but this is an overview of how exactly our CSMSCD used to work, what exactly is the concept of collision domain. This is bit of only history. We haven't spoken much about bridges, switches, or why the things would occur, or why there is a evolvement that has happened from hubs to bridges and bridges to switches. But this is the major thing, what used to be problem with hubs. So from hubs, the next thing which was introduced was a bridge, and from bridge the next thing which was introduced was a switch, which we are using even today. Now if we talk about Ethernet frame in detail, that's how your Ethernet frame ideally looks like. If we see from top to bottom approach, this data is nothing but what you are ideally getting from network layer or internet layer, and rest of the details are getting added, which is in different color, is getting added at Ethernet frame or at data link layer, out of which the most important aspects what you can consider is destination MAC address and source MAC address. Just now I have told you that MAC address is unique. MAC address is also known as physical address. This MAC address or physical address will be added in the Ethernet frame at data link layer. And then rest of the details are present, like preamble is there, SFD is there, destination MAC, source MAC, type which it defines, whether from top it is an IPv4 packet or IPv6 packet, and then whatever information you are getting at IPv4 and IPv6. And last one is FCS, which is the frame check sequence, which is used to make sure that the transmission between this is a switch, which is sending some data to this switch. It creates FCS value of, let's assume, I'm picking for a simplistic purpose, I'm picking some simpler values, which is 100. And when it would traverse over here, this guy would compare that what ideally should be the FCS value and what ideally FCS value it has received. So the FCS value of that overall Ethernet frame, if it is expected to be 100, but what it has received is maybe because of some integrity issues, because of maybe some CRCs, it got changed to 120, it will drop that frame. That's how your FCS is playing the role of making sure your frame is in good shape at layer 2 of OSI reference model. Okay, now the more important thing what I have picked up over here, or the word what I've used, is a MAC address. If we speak more about a MAC address, what exactly is a MAC address? Nothing but a representation of hexadecimal number, which is a 48-bit long. So when I say 48-bit, it can be in this format, like this, or it can be in the format of two and then two dotted hexadecimal format, like this way. Now, just now what I have shown you earlier, which is this is the one of the format what has been picked. Now, out of this 48-bit, how those have been divided, the first digit are associated with the vendor. The first 6 digits of the MAC addresses are associated with the vendor. Vendor means who is building that NIC card, or who is uh, manufacturing that NIC card. These first digits are also known as OUI. When I say OUI, they are also known as organizationally unique identifier. And the last 6 digit represents the NIC, which is uniquely within the OUI value. It means it would be individual representation of that NIC card. For example, if I pick up my NIC card, which is let's assume to be this one, I can find out who is the vendor for this guy. And all I have to do is maybe I have to go on Google and I have to say MAC address vendor lookup. So this any one website you can pick, and if I try to just copy paste this MAC address, it should be able to see what is the vendor. So my vendor is a Hi-Fi Electronics Technologies, who has built my Mac, who has built this NIC card. So this is for my physical one, which is my LAN based adapter as Ethernet. And if I go for wireless, then I would have this MAC address. And if I copy paste it, you can also do it for your own machines. That is not found. So it is not with any vendor. Maybe they have picked it up, or did I pick up the wrong one? Let me copy paste it again. Or maybe it is not with the database of these specific vendors. I can find out with some different one and give a try. So totally depends. You may not be able to find out with everyone. No assignment. So this has been, maybe internally my laptop is a Lenovo laptop and they maybe internally have done it, or it is not documented anywhere. That's why we are not able to find it out. But that is one of the way you can find out um, what exactly is a MAC address that it belongs to. This is a bit information about a MAC address, and every time an Ethernet frame is created, you will have to put the MAC address details into it. Now, if I go back, you will have to put a destination MAC address and you will have to put a source MAC address. Both MAC addresses are mandatory. You cannot play with this header. This header should be present as it is. Now, when you will learn more about how the flow works, when you will learn more about how end-to-end communication works, that time I'll explain what MAC address will be picked up in what scenarios. Now, few problems with limitation of, or what are the few problems or limitations of Ethernet, or one is a distance. We are very well aware that With respect to distance, because your UTP is having a very limited distance, at least 100 meters or 200 meters today. Earlier, it used to be in a bad scenario, or a lot of CRCs was being seen. Um, to solve this, and another problem was the collisions which used to happen at layer one hub devices, where they said that we will bring some intelligent device which will eventually not forward a frame on all of its interfaces. Um, we will have a better or easier way to forward the data forwarding, or how to forward the data. For that, the problem how it was solved was a bridges was introduced. Now, what are bridges? In simple words, bridge is another layer to Ethernet based technology device which will receive a frame. Now, when I say frame, it means it is data link layer. When I say packet, it is a network layer. When I say segment, it is a transport layer. So when I say frame, you have to imagine that, okay, I'm talking about data link layer. And the moment we are talking about data link layer, it means Ethernet, which is frame is always tagged to Ethernet. Now, what it does in simplest words is, let's assume this is my bridge and this is a PC connected over here, and this is another PC. Now with hub, what used to happen? This guy used to forward something and everyone used to get received. With bridge, this guy will forward it. Bridge will check where it needs to forward the data, and it will only forward to that interface. It will not forward it to everyone. That was the biggest achievement what they did with bridges. So intelligent forwarding is a correct word what I would like to use. Okay, this is what you call as intelligent forwarding. Now with bridges, if I go back and speak more, what exactly are other aspects in intelligent bridging? What they would do? They would perform the switching in software. Now, what do I mean by software? We are using mobiles, we are using computers, we are using laptop servers. Everyone have their own brain. That brain is nothing but a CPU. Same, your switches, your bridges also have their own brains, which are nothing but uh, CPUs, supervisors, and different names have been given to it. Now, every time bridges used to receive any Ethernet frame, it used to push that towards CPU. CPU used to open up the whole frame as per decapsulation process, what we have learned earlier. Then it used to check for destination MAC address, and then it would forward it towards destination. This used to hamper the device processing speed or processing power. Um, Now, this switching destinations, whatever frame is coming in on one interface, how it will be sent to which destination, that's where, as per the Ethernet frame, what we have just seen, it used to pick up the destination MAC address and it used to refer the local table. So we will talk about it in a moment, but on the basis of your destination, you are the forwarding of the frames are being done. Now with bridges, uh, you are switching now with bridges, every individual port is a part of an individual collision domain, which is an advancement from hubs and is a part of single broadcast domain. Now, what is a broadcast domain? I will talk about that when I introduce you to the concept of switches. Now, bridges ideally would perform three functions. Function number one, it will learn the MAC addresses. Okay, this is function number one. It learns every single MAC address. Function number two, it will forward the data intelligently with the help of destination MAC address. And type number three, it will help to remove the layer two loops. Now we will talk about every function individually, but let's pick up an example. Let's pick up the learning functions first. Now consider this is a small topology what I have. It means that frame would have MAC address. I'm just picking an example. The MAC address here is A, MAC address here is B, this is C, and this is T. The MAC address, what it will have as a destination MAC is, let's say C, and source MAC is A, which is its own MAC. Or let me reverse it from reading perspective. This is A, which represents this MAC address, and C, which represents MAC address which belongs to machine PC3. Now, when it will come over to this bridge, what it keeps is a local table, which is known as port address table. So what it will do, the first thing what this bridge, when it will open the Ethernet frame, it will see, okay, who is the source MAC? This is the source MAC. All I have to do is I will check the entry into my table. Do I have an entry present for source MAC address? No, in this case, we don't have any entry. So what it does, it says that, okay, if I want to go to MAC address A, I'm learning it. Let's say this is in this interface is 0, this is 1, this is 2, and this is 3. I have to go to interface or port, which is 0. This is the first entry what it has created. If the entry already exists, then what it says, it is resetting the timer. So that is having a dynamic timer. Let's say 300 seconds. And as of now, the timer is on 200 seconds left. So what it would do, the moment this frame is received with the same MAC address, if the entry exists already, it will reset this timer and make it to 300 again. Okay. And if the entry doesn't exist, then it will create a new entry and put a timer in that. Now, this is your learning function a bridge would do. And this is the same function what has been added in the switches, which you guys must be already aware about. I'm hoping that this is a moreover a refresher for everyone. Now, as the entry grows, if there are some stale entries, if the entries are passing post 300 seconds, they will be deleted automatically. So these are dynamic entries which are present in port address table. This is the first function what switch would do. Now, function number two is forwarding function, which is how this bridge, not switch, how this bridge will forward the frame towards the actual destination. Because as of now, to forward the frame towards actual destination, it goes and check the destination MAC address. The destination MAC address is C, which this bridge is not aware about. So whenever a bridge is not aware about any entry, what it will do is it will flood that frame out of the port. So it is flooding it everywhere. It is flooding here, it is flooding here, it is flooding here. Out of all ports, it is flooding except from the port where it has received it. So with the help of this, what exactly have happened that now the actual frame which was originated by PC1 has reached out to PC3, and whenever PC3 will now create a reply, what it will do, now this is my source. This is my source and this is my destination. Though my source is C, destination is A, and when it will go back towards switch towards the bridge again will perform the same function. What is the function? It will pick up the source. Source is C, it don't have an entry, so it is creating an entry that if it wants to go and learn uh, reach to MAC address C, it has to go to port number 2 and entry will be added. And it will refer for destination MAC address and it knows, okay, my destination MAC address is A. And if it has to go to destination MAC address A, the traffic should traverse towards port 0. This is the intelligent forwarding of data or forwarding as a function that is achieved by the bridge. Understood? What are the two functions done? You can at least raise your hands. Thank you. Now the third functionality is avoiding the loops. Now in first case, why the loop would be occurred, or why a simple loop would be occur in layer 2 domain. Uh, Let me give you an interesting fact. Let's assume this guy sends up some broadcast, or I'll simplify the diagram for everyone's sake. I'll better use some better simplest diagrams. So let's say this is my bridge number 1, and it is connected on two different interfaces. I have a PC1, I have a PC2. Now, this PC1 generates some kind of broadcast. What is broadcast? It means a type of frame or a packet which is intended to go everywhere, which is supposed to go, it has been generated for a reason that it should be reached to everyone. Let's assume this hypothetical situation. So it reaches to my bridge one. What bridge one does? What is the rule of a bridge one? Just now we have seen. First, check out for source MAC. So I know what is my source MAC here. It will make out all the details, then it will check for destination MAC. Destination MAC, let's assume to be something as a broadcast, which we will speak in sometime. Some MAC address, which one is not aware, which bridge one is not aware about. So what bridge one does, it puts it on both of its interfaces. So it puts it here, and it also puts it here. It reaches to bridge 2. Bridge 2 also performs the same function. It performs the source MAC address learning, which is learning function is done. It will do the forwarding function. Now, while doing the forwarding function, the most important thing what it does is it don't know where to forward. So what it does, it do the broadcast of the frame. And it does this as the same hub functionality, which is anything which is received on an interface will not be sent back to the same interface. It means, let's assume I'll represent two different colors for easy understanding. This is a frame with yellow color, and a frame with pink color. So frame with pink color has landed on Ethernet port 0. So the port on both sides are 0 here, and the port on both sides are 1 here. So the Ethernet frame has landed on port number 0. The rule says it will not be sent back to the same port. That is, we are already aware. So we don't have any problem. We will not forward it. But it will be forwarded out of all interfaces from except where it has been received. So it would be forwarded here, but eventually would be also be forwarded here. This is my frame number with pink color. Now consider second scenario of frame which has landed on yellow color. Will do the same functionality, that will be forwarded towards the PC, but it will also be forwarded towards port number 0. Now, these frames will eventually reach to bridge 1. And what bridge 1 will do is the same function. A frame which is landing on port number 0 will be forwarded towards port number 1, and a frame which is landing on port number 1 will be forwarded towards port number 0. So if you see, this process will keep happening considering a loop gets created, loop of frame, and this loop of frame is production impacting or traffic impacting. Why? Because remember, bridge means processing of the frame happens in CPU. If you are receiving too much of frames at CPU level, and if you are CPU is not capable to handle it, it will start going in performing unexpectedly, which is nothing but what high CPU cases what you see. High CPU is because your CPU is getting too much of traffic, which is it is not capable to handle. Same thing happens with your laptops, mobiles, everything. Now, this to avoid to avoid such scenarios, and those scenarios are avoided with the help of a protocol called as spanning tree protocol. Again, this is how your loops are avoided, be it by the bridges, be it by the switches. But uh, this is a job of loop avoidance, which is the third function any bridge would do. Now, you have learned about bridges, then you would say what exactly was the need even to have switches? Anyone? Any clue? Good. Switches operates exactly like bridges, but in a better way. So in simple words, you are having two phones. One is an iPhone, one is a OnePlus. I'm not branding anyone, but maybe let's assume that iPhone performs both do same functionalities. Both are capable to handle click the pictures, send the emails, WhatsApp support, and everything. But still, one's performance is better, one's performance is less. Why? Because how the mechanisms have been developed, they are doing the same functionalities. Switches is a evolution to bridge. Now how switches are evolution to the bridges? With the help of this one liner, which is the forwarding decisions in switches are done in the hardware. So in the bridges, the forwarding decisions used to be in the software. So every time your CPU was engaged with switches, what they said, we will bring mini CPUs on every port. Or let's say we will allocate mini CPUs to some 5, 10 ports. So let's assume if this is my one big switch. Okay, I'm not able to. So let's assume this is my switch, it having multiple ports, and it is having one CPU, which it was to be the bridge condition. But what they said, with every 3 ports, we will have one mini CPU. So every time you will not have to go to main CPU to perform the things. And these CPUs are nothing but your application specific integrated circuits, which are nothing but ASIC. So ASIC is a chipset or specialized processors which are used or which are built to perform very few tasks. Like very few tasks. What is the task in this case? Maybe let's say if some frame is coming, it will check for destination MAC address and forward the frame to whatever is a port. So only port address table is written down or it is maintained in the ASIC. Now, with respect to bridges, what you used to call a port address table, in switches we called it as a MAC address table or CAM table. Same name. CAM, the full form of CAM is a content address memory table. Now, uh, switch again is a part of same broadcast domain. Now, what is a broadcast? We will talk about it. But having an individual collision domain on every single port. Now, what are different type of or methods of switching those are being performed? If we talk, there are 3 different methods of switching. The method first method is the switch receives an Ethernet frame, and as soon as it sees the destination MAC address, it will refer where it needs to be forwarded, and it will forward. So with cut through switching, your forwarding is very fast. So in data centers, let's say with financial institutions, you would see a forwarding being done or where you want very less cut through switching is being used. Uh, it is a store and forward where where the switch will wait before the whole frame is received. Once it is received, then the first thing what it will do is it will do the FCS check. What is FCS check? Thus now we have seen frame check sequence, which is the integrity of the frame, whether it is corrupted or not corrupted. This is part two what it will do. And once FCS check is done, then it will forward it towards the destination. This is type number two. Type number three is a fragment free. So it is a nothing but a combination between cut through and store and forward. So what it does, fragment free reads first 64 bytes of the frame. Ideally, frame, and when the destination MAC go with first 64 bytes, and which includes your frame header, and switching ideally begins before the checksum are read. Now if you remember the Ethernet header what I have shown you, FCS is at last. Now, if I imagine this like this way, and if the frame is entering from here, assume this, FCS will be checked at last. So what will happen with cut through, the moment frame enters till destination? Imagine this is your Ethernet port. Imagine that it enters till destination, cut through will forward it, check it and forward it ahead. With store and forward, it will read the whole frame. And third one is, which is just now what we were seeing, in which it will read for first 64 bytes. So some bytes of it plus this byte. So once this is received, it will forward it. It will not wait for FCS check. These are the three different switching mechanisms which are implemented and supported in today's switches. Next concept is duplexing. Now, duplexing is something in which how a device can send or receive the data. There are two modes of duplexes. First is a half duplex and second one is a full duplex. So with half duplex, either you can send the data or you can receive the data at same point of time. With full duplex, you can send the data as well as receive the data. Simplest example happens to be half duplex. Whether you could send the data at any point of time when you were sending it, rest of the people were receiving it or listening it, or rest of the devices were listening it. Whereas full duplex, a switch, an interface of the switch, it can receive a data at same point of time as well as it can send the data at same point of time. That is a difference between a full duplex and a half duplex. Now, again, coming back to the functionalities of switching, it will do the same three functions. Learning, which is the same function what you have in bridges. Forwarding, same function what you have in bridges. And third one is removing layer 2 loops with the help of spanning tree protocols, which is same thing what you have seen in the bridges. But the bigger difference with switches and bridges are collision domains, processing in the hardware, not collision domain, processing in the hardware versus processing in the software is the biggest uh, difference. And because I haven't spoken about broadcast domain yet, I'll talk about that in some time. That time you will understand how switches have evolved in a better way as compared to bridges. What are the Ethernet frames? Ethernet frames, different type of Ethernet frames, if you know, those are unicast, multicast, and broadcast. If you already have an understanding around it, what type of situations are there where you will use unicast or broadcast or multicast? For example, unicast means with a unicast, source would send 50 copies of frame individually to its destination. So when I say that, let's assume this is a source who is trying to send some kind of data. This is my switch. this is destination 1, destination 2, destination 3, destination 4. So now, not 54 in this case. So this is for D1, this is for D2, this is for D3, and this is for D4. So this is moreover a one-to-one communication which is being achieved between source to destination. This is communication 1, communication 2, 3, 4. This is nothing but your concept of source. Next is multicast frames and broadcast frames. So broadcast frame is a frame that would be sent to all devices in the broadcast domain. For example, switch needs to a machine needs to send a same copy of data to all the destinations in the same group. So what it would do, it would use the destination MAC address FFFF, which is nothing but a representation of broadcast MAC address. And it would send it to every individual port. And when switch will receive this frame, switch will check for destination MAC, because destination MAC belongs to FFFF. It will understand that this needs to be broadcasted, and it would be sending it to all of the frames, all of the interfaces. Third one is a multicast, which is a frame is addressed to specific set of users, not all users. So if I just pick up an example, consider this is my again source, this is my switch, right side represents all the receivers. So with broadcast, what it does, whenever an Ethernet frame is generated, consider this is source. So the MAC address here is A, which is 48-bit. So repeat this 3 times. This is A. Okay. Now this 4, this is my source MAC address, and this is my destination MAC address. So destination MAC address, whenever I want to do the broadcast, it is sending it to all F. It is getting landed over here, and what this switch does is it forwards this specific kind of data to all of the ports. This is a broadcast frame. Versus the third type, which is your multicast, which is source here again, sent it to switch. Switch is having multiple receivers, but only few are interested to receive the frame, not all. So multicast is one to many, not one to all. What it would be done, it would be sent over here, and the switch will forward it only to interfaces where the receivers are interested. These are the 3 type of frames what are being used. Now you have to understand the beauty whenever I introduce you to the concept of layer 3s, how layer 3 are getting integrated with layer 2s. Understanding that aspect is very important. I hope this is clear. Now, what are certain MAC addresses which are used in certain scenarios? Now, consider it like this. I have picked up one example, which is whenever your destination MAC address is used as all F, then it is a broadcast. So consider this frame. This is a packet capture what I have done, in which the destination broadcast is FFFF. So it means it is supposed to be sent to everyone. Second one is a multicast. Whenever you have few users, this is a range what will be used. Something from this range will be used. From 0100 to 5E00.0000 to 0100.5E7F to FF. This is a range which will be used whenever you are using some multicast. But at layer 2 multicast, how things will work versus how you will go one layer ahead, which is network layer, we will integrate them later on. Now, unknown unicast destination, in which if you don't know where exactly is the destination lies, then you will use unknown unicast. So what you will do in that case, if you don't know where is the destination, you will forward it to all of the interfaces. But it is not a broadcast. It is an unknown unicast. And this is where, if you have observed, we are doing too much of forwarding of the frames, which we want to avoid. And this is moreover because of one single broadcast domain, which is a limitation what we have as of now, which we will tackle in some point of time. Now, how does Switchwood learn the whole scenarios? Just now we have seen, whenever a PC learns the MAC address, whenever PC tries to send something and switch learns it, it adds the entry into the CAM table. So the MAC address here is this AA, and it is being learned on port number 1. Same way when this guy sends some data, because what Hub would do, Hub would broadcast it everywhere, and this is also being learned on port number 1. Same way C is also being learned on port number 1. E is being learned on port number 4, and F is being learned on port number uh, 2. What would happen if a user is coming in with a source MAC address of A, which is this? Imagine this is my source MAC and destination is F. So what it would do? It would come over here and it will say that, okay, my source MAC address I already know. I just have to reset the timer, and destination MAC address I already know. So I'll forward the frame towards this guy. So this is a unicast forwarding pattern. Okay, now second situation. Instead of this F, I mean not a single F, it is all broadcast. So F, 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 port 3 times. If it is coming from PCA, landing on switch 4, what switch 4 says? It checks again for source MAC address. It understands that, okay, my source address is A, destination MAC address is FFFF, which is a broadcast. Then it should be forwarded everywhere, except the port where it has received. So it will not be forwarded on switch 1. This type of forwarding is your broadcast. Third type is unknown unicast. Now, I am not going to talk about multicast because we are going to speak about multicast tomorrow. It is not a part of Ccna as an overview, and that would be too much of bouncer before you guys have a quite understanding on routing as an aspect. So I will not talk about multicast max being used, but the third scenario is, let's assume my source MAC address is again A. Source MAC address is again A, but destination MAC address is T. When it comes over here, repeat the process. Your source MAC address entry will be checked. If the entries are present, the timers are resetted. If the entries are not present, then uh, next thing is, it will add the entry into the CAM table and then check for destination MAC. Now it don't know where is the destination MAC present. And that's where it will do the unknown unicast flooding. So what it will do, it will forward it to all of the ports. This is a unknown unicast flooding. That is the difference in broadcast versus in unicast. Any doubts, feel free to put it in the chat. Layer 2 loops, we just have seen the layer 2 loop on, how it is avoided. Same logics are applicable even for um, switching. No difference on how STP is implemented. STP we will talk probably today or tomorrow. I guess today only we will talk about it. How STP is helping to avoid the loops, that is altogether a different topic. But now this is where I introduce you to the next concept, which is I have been constantly speaking about one word, which is broadcast domain. Now, when I say broadcast domain, which is a single broadcast domain, what is a single broadcast domain? Consider this again is a switch. My machine one, machine two, machine three, machine four. By default, we are every switch is a part of one single broadcast domain. It means, let's assume if my PC1 generates some kind of broadcast or unknown unicast, it will be forwarded to all of the interfaces. This is moreover, choking your bandwidth for no reason. Why it would be forwarded to all of the interfaces? Because they are a part of one single broadcast. Now, I hope you understand the word broadcast means that if any kind of broadcast is coming in, it will be sent out to every single interface. That's where I will be sending it to every interface, which may be necessary, may not be necessary. In such case, what you would like to do? We want to reduce the broadcast to save the bandwidth, to save a lot of collisions happening because of too many broadcasts being pushed to the device. Please extend unicast. Yeah, unicast is where the communication happens between one source to one destination. That is unicast. So let's assume this is my PC1 wants to talk to PC3. The communication from PC1 to PC3 is a unicast communication. So in simple words, if I write it down, unicast is one-to-one communication. Broadcast is one to all, everyone communication. And third one is multicast. It means one to many, but not everyone. Is it understood? Perfect. Now, what we are talking that unnecessarily a machine is generating something by PC1 is generating and you are forwarding everywhere, which I don't want to, which I know that it is not a feasible solution. So what concept was introduced to reduce the broadcast domains? That concept is a VLAN, virtual LAN identifiers. What virtual LAN identifier ideally does, it reduces your broadcast domain. So as of now, if I again draw the simple diagram, so virtual LAN identifier in simple words is nothing but a numeric value which we are assigning to uh, an individual port. For example, consider this 4 device topology, and I am introducing you to the concept of VLAN, which is virtual LAN identifier. Now, virtual LAN identifier is nothing but a numeric value. Numeric value means some number. Okay. Now, imagine I am allocating this port with a number 10, with a port number 10, which is VLAN 10. And here, which is VLAN 20, and here it is VLAN 20. So what have you done? You have reduced your one single broadcast domain into two different domains now. What are two different broadcast domains? Broadcast domain number one, whose representation is done with a VLAN value of 10, and broadcast domain 22, whose representation is done with a VLAN number 20. Now, what will happen? Any broadcast generated by switch 1 will come over here. It cannot go towards another broadcast domain. It can only penetrate into its domain. Clear? What exactly is the logic? So in simple words, if you want to, if everyone is working, if you want to talk to your peer who is in your team, you can directly go. So in simple words, if this is, I'll pick up some names, don't get offended. My name, let's say this is Sumit, wants to talk to Anish. We are a part of same team. We can directly go and talk to each other. But maybe let's say um Rafi wants to talk to Prashant. They can talk to each other without any problem because they are a part of same team. I'll do that. Give me a moment. Now consider Prashant and Rafi, they are part of same team. They can talk to each other without any intervention. Sumit and Anish can talk to each other without any problem. But what if Sumit wants to talk to Prashant? They cannot talk. They cannot talk directly. They will have to go via the bosses, which is they will have to go one layer above, which is layer 3. That's how they can talk to each other. Now, repeating this concept one more time. Have everyone understood that why a switch have one single broadcast domain? Is that understood by everyone? Now we want to break the broadcast domain. What we want to do, because to avoid the unnecessary flooding, what we want to do, we want to create smaller domains. So what I do, I create broadcast domain number 1 and I am allocating it to VLAN 10. So VLAN is nothing but a full form of VLAN is a virtual LAN identifier. VLAN ID is a full form, VLAN ID, virtual LAN identifier. So what does VLAN 10 represent? VLAN 10 represents a set of users who are a part of same broadcast domain. Clear till now? What does VLAN ID represent? And then you have another set of broadcast. BD is a broadcast domain in simple words. Um, is this another set of users which is BD2 which are mapped to VLAN 20. But how will you differentiate it here on the switch? So what you do, you go on every single switch here and you tell them, okay, this interface is a part of VLAN 10. This interface here is a part of VLAN 10. This interface is a part of VLAN 20. This interface is a part of VLAN 20. Now, what have you done? Have you created two different broadcast domains? Whereas your PC1 and PC2 are part of one broadcast domain, and PC3 and PC4 are part of another broadcast domain. Is it clear now? What does VLAN will help you to achieve? Perfect. Now, this is the job of VLAN, what exactly it is doing, and it is helping us to do the segmentation or to form the broadcast domain to reduce the unnecessarily broadcasting. Okay? VLAN is nothing but a logical segment. Now, in other words, VLAN is a logical grouping of end host. If you see here, PCA, PCB, PCE, PCF, these four guys are part of one common VLAN. Let's say this is VLAN 10. PCC and PCD are part of VLAN 20, and here they are part of VLAN 30. Now the beauty is you can extend switches. Just now we have seen what the switches do. Switches will help us to create the VLANs, and it will help us to create to separate the broadcast domains. So this VLAN as a numbering or any configurations with respect to VLANs will be performed on the switches to put this specific to put the specific machines into individual VLAN. So what you will do in simple words, you will go in this switch, you will say VLAN 10. So you have created a VLAN and you will say this port is a part of VLAN 10 now. This port is a part of VLAN 10. So have you put these PCA and PCB as a part of VLAN 10? Is it understood? Any doubts? Okay. Moving ahead, this will be the job which will be done by the VLAN. But now, next thing what I'm going to introduce to you is when we are dealing with VLANs, what type of ports we have. Now, ports means what? Uh, you have a switch. I'll show you the switch also. If you check this diagram, this this is a switch. This is one of the switch, and if you see here, these are the ports. These are Ethernet ports where you can where you can plug the cable. So consider this is going to PCA, this is going to PCB, same way this is going to PCC and so on. Every port is going to one physical cable, is going to one Ethernet port on the switch side, and another that cable's another side is going to be your machine. Now there are two type of switch ports what we ideally have. First is a access link and second one is a trunk link. Access link is a connection, or access link connection is a type of connection where the remote sites are connected to end host machines. When we say end host machines, in simple words, uh, they understands only plain Ethernet frames. They cannot bear any changes in the Ethernet frames. When I say they cannot bear any changes in the Ethernet frames, by that means whatever Ethernet frame I have shown you, they only understand that. Any tweaks if you do in the Ethernet frames, they will be not able to understand that. Okay, so those are what kind of devices? Any end host machines, any computers, laptops, printers, are devices which understands only standardized Ethernet frames. Now, whenever you are connecting a switch with a PC, you will configure that specific port as what type of port. There are two type of ports we have seen. Just now we are talking, one is a access port and one is a trunk port. So what type of port it would be? It would be access. I hope it is clear what type of port you will connect. It is access. Now, if I connect a router over here, what type of port will you configure this? Good. Anyone knows? A router works at what layer of the OSI reference model? Layer 3. So if it is a layer 3, it will understand understand only standardized Ethernet frames, not any tweaks which will be done in the Ethernet frames. So these tweaks cannot be understood by the router. Hence, what you will configure here is the access port. There are some deviations into that what you can achieve. I'm not denying it, but as of now, keep it in mind that ideally, out of 10, 8 times you would end up configuring the port which is facing towards the router as an access port. Now, what are trunk ports? Another important thing what you have to understand that trunk ports are ideally configured whenever you have two switches connected to each other. Whenever you have two switches, then you have trunk ports that needs to be configured. Now, what is the reason behind it? Let's talk about that. Consider this is my one PC who is a part of VLAN 10. This is my PC1. This is my PC2. This is PC2. This guy is also part of VLAN 10. Now, what I told you, we have created a broadcast domain. What is a broadcast domain? VLAN is a logical separation. Now, if you are sending some data on P2 from PC1 destined to PC2, it enters on switch 1 as a part of VLAN 10. Will it get forwarded ahead on this interface? What if this guy here is a part of VLAN 20? Any traffic coming from VLAN 10, can it enter into VLAN 20? Yes or no? I'm hoping that is understood that it cannot. That's why we are doing a logical separation of the VLANs or logical separation of our interfaces with the help of broadcast domains. This is my third machine, PC4. Now to achieve this communication between PC1 and PC2, the solution what I can have is I should have this interfaces on this side and this side also as a part of VLAN 10. Then only they will be able to talk to each other. How the communication will go from PC1 to switch 1, switch 1 to switch 2, and switch 2 to PC2. But the problem is this is one-way communication. This is only for VLAN 10. What if on the same switch I bring another user who is a part of VLAN 20? And here also it is a part of VLAN 20. Now in this case, I also want to make a communication from PC3 to PC4, but I only have one link who is configured to access or to allow traffic for VLAN 10. So the solution in that case is I will add one more link. And I will say this is a part of now VLAN 20. This is a part of VLAN 20. Everything is going hunky-dory. There is no problem. But the challenging aspect is what if I introduce one more over here, and I keep introducing more machines on different VLANs. Every time adding a cable between the two switches is not going to be the feasible solution. So what exactly is a do? is to introduce the concept of trunk. What trunk will do, trunk ideally helps or capable of carrying traffic for multiple VLANs. So it carries traffic for VLAN 10, it also carries traffic for 20, it also carries traffic for 30, 40, and so on. This is what trunking does, carries traffic for multiple VLANs. But to carry the traffic for multiple VLANs, your Ethernet frame needs to modify and VLAN information needs to be added into your Ethernet frame. Then only receiving switch will understand that, okay, this traffic is coming for VLAN 10. Okay, this traffic is coming for VLAN 20. And this modification of the Ethernet frame is done with the help of trunking ISL, which is inter-switch link, and second one is IEEE 802.1q, or also referred as .1q, out of which this is obsolete already. So what we have is 802.1q. This is how you will send the traffic on a trunk link. And trunk link will receive a traffic and then forward to individual switches. Is it clear what is access port and what is trunk port? Next is VTP. So we are just, touching bases on multiple aspects. Uh, Go and ask the question, please. Muhammad Mafazur Rahman, feel free to ask the question on the chat. Not sure why you guys are not able to unmute, but initially someone did it. Yeah, I guess there are no questions. Now, imagine you are creating VLAN because the first step on switch is you will create a VLANs. Now, in real life scenarios or in production networks, uh, you don't have one VLAN. You have a dedicated VLAN for different type of users. Like if I pick a few, I'll say that for my VLANs, for my data, which is to my laptops or to my um, desktops, what you have in office, there is a dedicated VLAN called data VLAN. Data is a name to it. Maybe the VLAN allocated to that are 10 and 20. So all I have to do is go under the switch, go to config mode, and I have to say VLAN 10 and name it as data. Giving the name is not compulsory. It is for our own ease out purpose. Same thing I'll do for VLAN 20. Name is data, something like that. Now, let's say for voice, because you must have a voice over IP phones into your office, I'm allocating VLAN 30. So I'll say VLAN 30, name is voice. Let's say you have printer, then you have CCTV, you have biometric, and so on. Many examples. Okay, you have too many VLANs. Now, you have to go on every single switch and you have to configure the VLANs. It is not like if you have only, um, you know, four switches, you have users connected over here, everywhere. It is not like you will only connect it on one switch and that will suffice your requirement. No, it is not going to happen like that. You have to configure the VLANs on every single switch. Now, the problem with this is you have to do too many configurations. Let's say you are having 10 VLANs allocated as per your network's requirement and name to every VLAN. So It means you have to perform 20 lines of configurations on every switch multiplied by 4 equal to 80 lines of configurations. What you have to do on all of these four switches. And imagine if you have 10, 15, 20 odd number of switches, then the challenge would be bigger. So what ideally is a solution in such case is called as VTP. So VTP is nothing but a Cisco proprietary protocol. When I say Cisco proprietary, it means only this can be implemented only on Cisco devices, not on any other vendor devices. Um, One guy will configure the VLANs, and that VLAN information with the help of VTP packets will be sent to other switches in the network. So for example, imagine this is your these are your 3 or 4 switches connected to each other. So imagine those 20 lines you configured on switch 1, and with the help of VTP protocol, it got advertised to switch 2. Switch 2 will advertise that to switch 3. Switch 3 will advertise that to switch 4, and so on. It will keep happening all time. But the most important thing what you have to keep in mind is the this information will be only exchanged on the trunk links. So for example, because of some reason you have kept as this as access link, the VTP information will not get exchanged. Now, I had told you that you have to configure the trunk in between two switches. If this is what you have programmed in your mind, uh, the important thing what you have to understand is you should configure the trunk whenever you want to send the traffic for multiple VLANs. What if your requirement is quite simple that you have two switches and there are only two users connected to them or two servers and they are part of VLAN 10. And this specific connectivity is only being used for, let's say, data backup. Maybe this is our active server who is constantly sending some data as a backup to the backup server. And there are no other devices in this case. So what you would do in such case, do you need a trunk link? As of today, don't consider about future aspects. But if I ask you, if you have only two users, both are part of VLAN 10, what is the type of connection you should form between switch 1 and switch 2? Would it be trunk or would it be access? Any clue? I'm considering no. Yeah, okay. Someone has given trunk. Is it mandatory that you have to configure a trunk? You can configure a trunk. Is it compulsory that you will have to configure the trunk? No, it is not mandatory. Correct. So you can also configure it as access. Now, if I introduce two more servers here, and these are part of different VLANs, VLAN 20 here and VLAN 20 here. Now it becomes mandatory for you to configure this link as a trunk because you want to send the traffic for two different switch type, two different VLANs. I hope is it clear? Now, whenever you are configuring the VTP, you have to make sure that the information related to VTP will only go on the trunk links. It will not go on the access links. There are three different modes what you can run in VTP, which is client mode, server mode, and transparent. Now, what are the differences between client, server, and transparent? If I just pick up a diagram, easy to explain. So assume this is my switch who is configured with VTP mode as a server. This is configured as a client. This is also configured as a client. And this is configured as a transparent. Now with server mode, you can create, modify, delete VLAN information. So you will create the VLAN over here. That information will be passed to switch 2, switch 3, switch 4. How individual switches will act on it, I will talk about it. But creation, modification, deletion, any kind of changes can be done on server VTP switch. Client switch will only receive from server. You cannot make any changes on receive from server. You cannot make any kind of changes on client switches. And again, when client switch 2 receives this information, it will relay that information to switch 3. Relay means it will forward that information to switch 3. Now, the same information what server has created will go via BTP message to switch 4. What transparent switch will do with the information what it has received from server. Transparent says I am rebel. When I say I am rebel, it means I am not going to listen to you. Whatever information you are sending it to me, I'll just ignore it. So on transparent mode, you can create your own VLAN information. You can create, modify, delete, everything can be done. But it is local to the switch. It will not take effect on anyone else. So imagine there is one more switch over here, which is switch 5. So whatever changes you are making on switch 4, those will not have any impact on switch 5 or switch 1. This is your third type of BTP, three different type of BTP is what you see. So if you see the summary over here, see this. Can modify, delete VLAN, server, yes. Client, no. Transparent, yes. Can generate VTP message because VTP is nothing but a type of messages, type of a protocol. When we say protocol, it means rules. When we say rules, it means there are some predefined set of logics. So you can generate VTP messages, only server can generate. No client and transparent can do it. Can propagate VTP messages. Propagate means if you are receiving it from one switch, let's say if this switch is receiving a VTP message from someone, will you send it ahead? That is a propagation. Okay. Can accept changes in VTP message? Yes, server can do it, client can do it. Transparent cannot do it. Default VTP mode on all the switches are server, what do you call it? Server mode is a default mode whenever you enable VTP on any of the switches. So by default, whenever you see it. Is it good? Next concept is a DTP. Another Cisco's proprietary tool which will help you to negotiate the trunk between the devices. Now, what I have told you that trunk propagate means sending from whatever you are receiving from one device, you will forward it to another device. It's like a WhatsApp forward. You receive it from one and you forward it to another one or someone. Clear now? Now, DTP, just now I have told you that IEEE trunking protocols have different modes like ISL and 802.1q, out of which ISL is already end of support and 802.1q is currently used in the market. Now, when I say end of support, it means in the newer devices, you will not see it. If you bring some old device, old Cisco switch, you will still see it. But on older Cisco devices, you will not find any of the switches supporting ISL as a protocol. That is what I mean by end of support. Now, it have five different modes: on or trunk mode, desirable mode, um, auto mode, no negotiate mode, and off mode. And you configure it on both sides or one side. Um, that's how other side will take care of. So, for example, on one switch, imagine this is one switch and this is other switch. So if you configure one side as on and other side as on, it will form the trunk. If you configure one side as on, other side as desirable, it will form the trunk. If you configure one side as on, other side as auto, then it will form the trunk. Second, if you configure one side as desirable and other side as on or desirable or auto, then only it will form the trunk. These are the probabilities which has been written down. And this concept is called as dynamic trunking protocol. Go on. Any kind of doubts? Okay, if no doubts, our next topic is spanning tree protocol. But before we start, we will have a quick lunch break of, let's say, 45 to 50 minutes. So maybe we will reconvene at 14:35, I would say. If I'll just write it down here. So this ideally gives us 45 minutes break for lunch. See you in 45 minutes. STP was designed only to avoid the layer 2 loops from the topologies. But to do that, switches have to share some information about themselves to the connections. And those informations are ideally being exchanged with the help of BPDUs, which are bridge protocol data units. These are sent out to as a multicast frame on the layer 2 switches. It means it can never cross an L3 boundary. So if I just draw a small topology and whatever is your understanding, but if I ask you that, let's assume these are four switches connected to each other, and this is a router, and below the router you have another setup with another few switches. The question is BPDU, which is generated, let's assume by switch 1, will it ever reach switch 5, 6, 7, 8? Any clue? Question is BPDU generated by switch 1 when it will go towards the router, will it forward it ahead here? BPDU is again a part of a data link layer, and it basically forwards or goes with a MAC address of multicast. Now, router, whenever see something like this or any L3 device, when it sees a frame with a MAC address of multicast, it will drop it. This is the default behavior, and there are some deviations in that, or predefined MAC addresses, not the multicast MAC addresses, but these are predefined MAC address. What we have, like BPDU, have a dedicated predefined MAC address. Now, how spanning tree will avoid the loop? Basically, once BPDUs are learned, BPDUs are exchanged, uh, they will decide that out of the loop or out of the topology, they would want one port to go into blocking state. So for example, the previous topology we have seen, these are two switches, and when we enable or when we start spanning tree protocol, which is the default mechanism, spanning tree runs by default on all of the switches with Cisco. What it would do, it would put one of the port into blocking state. And this is a logical blocking. When I say logical blocking, what do I mean by that? It means if this port is into blocking state, traffic would traverse via the this link. And because of any reason, if my this link goes down, then this port would start going into forwarding state. Which is now it will assume the role of actually being the forwarder. So this is a logical blocking. And it will be only into the blocking state until there is some alternative link which is carrying the information and doing the job what it is expected to do. Now spanning tree will put this port into blocking state, and how spanning tree decides or what are the logics behind those on which port to go into the blocking state, there are certain rules. So basically how spanning tree avoid the loops. To avoid the loop, first thing what switch does is it selects the root bridge. What is a root bridge? In simple words, is consider that this is my three switch topology, and for sure there is a loop which will occur in this case. A frame coming from here will go here, will come here again, will go here, and same way. So what these guys will do, it will select the root bridge. And a root bridge is nothing but a master or a Spock, I would say, from this domain perspective. From this topology perspective, there will be one guy who will be master. And how this master will be selected? There are rules to select the masters or to select the root bridge. What are the rules? Rule number one says, I'll check the priority. So what will happen? Switch one will send a BPDU. This BPDU IDD contains the information about priority and all those things. So let's assume switch one is having a priority of some value, maybe 100. These are not actual values. I'm just picking it up for understanding purpose. So these is a priority value which is present on every switch 100, 200, and 300. So priority will be checked between the three switches. Out of these three, switch one is having the least priority, hence it will become the root bridge. But what if your priority is a tie on three sides? It is 100 over here and it is also 100 value over here. If the priority is a tie, then lowest MAC address will be chosen. So this is lowest priority will be chosen, who will become the root bridge. Lowest priority. Lowest MAC address will be selected. And the information about the MAC address and priority on all other details are going in the BPDU packet. That's why the BPDU needs to be exchanged. Now, in this case, if switch 2's MAC address is lowest among the three, then switch 2 will become the root bridge. Now, with respect to priority, the range varies from 0 to 65535. This is the range in which priority will exist. It is always in the multiplier of 4096. So either first value is 0, then second value is 4096, third value is 8192, and so on. So this is 0 plus 4096. 0 plus 4096 become 4096. 4096 plus 4096 becomes 8192. So it is always in the multiplier of 4096. And the default priority of every switch is 32768. This is how you will choose the root bridge. I hope it is clear. Now, second concept in this is port rules. What are port rules if we talk in a simplest words? That once you have selected the root bridge, what are the different type of roles which will be assigned to the ports? And on the basis of that, you will see what port will go into the blocking state. So there are three different type of uh, however, there are three different type of roles which are port roles what we have seen. The first one is root port. So root port is a port which is pointing towards the root bridge from a non-root bridge switch. When I say that, if we try to determine it in a diagram manner, consider it like this. I imagine these are my three switches. And these are my priorities. Now, if this is a scenario, who will be the root bridge? Can anyone tell me? If priority is a tie, which is in this case is what happening, then lowest MAC address will be selected, and that's why switch one is considered to be the root bridge. Now, the definition, what we have seen, the first definition is the RP, which is a root port, and root port is nothing but a port which is nearest port bridge or switch, whatever word you want to use. So if you see, if this is your root bridge, then the nearest port is going to be this port as well as this port. These are the nearest port to the root switch. And how it is decided on what basis it is decided, not on the visuals of the diagrams, but there is a logic behind it. There is a concept of cost involved in it, which we will talk into tomorrow's session. But if you see, this is what your ports would look like. These are your root ports. This is type number one, which is the root port. If you go and check out second type, which is designated port, a port forwarding data towards downstream switches when received from root port. So when I say that, and if I show you again, port which is forwarding data down towards downstream switches. So consider there is one more switch over here for simplest understanding. Any data which is received on a root port will be forwarded towards downstream port. So this specific port where you're forwarding the data is nothing but your designated port. From your root bridge perspective, all the ports of the root bridge ports are always designated ports. So designated means forwarding ports. Root ports means forwarding ports. Their state is forwarding. And third type is, this is designated port, what we have seen. It forwarded port from, this is one definition. And then another thing is, on root bridge, all ports are designated ports. Now the third port type, which is blocking port, is nothing but a port which will ideally help us to avoid the STP loop. This specific port will not send any kind of data, nor it will receive any kind of data. When I say data, it means actual data, not the control plane data. When I say control plane, not the BPDUs. It will keep listening to the BPDUs on that port. Now, out of these two ports, out of these two links, one link would be going into the blocking state. Let's assume, I am saying assume as of now because tomorrow I'll be explaining you why this port has been selected. But this port will go into this port will go into the blocking port, and this port here would be going into the designated forwarding state. This is how STP. Now, if you see in this case, my one port has gone into the blocking state, and the traffic, any traffic coming from anywhere will not get forwarded because of this one blocking port. This is a whole logic which is being implemented uh, or being followed from STP's perspective. And this is an example what we have seen how the loop is being avoided. Any questions? Moving ahead, next topic what we have is called ether channels. Now, if you see the diagram on the right side, what will happen in general case? Anyone knows? Two switches connected back to back. These one port will go into blocking state. One port here will go into blocking state. One port will everywhere will go into blocking state. Now imagine from downstream you are getting too much of data, and distribution from distribution layer, if you want to go upstream towards core, and if you want to use both of the uplinks. Because if you have that handy with you, why you would not want to use it, right? That is the simplest logic, that if you have two 10 gigabit links, you would surely want to use both of its links. But because of STP, one port would go into the blocking state. Now, to mitigate this problem, only with two back-to-back or three back-to-back links, uh, how you can achieve it is you can use ether channel to achieve the higher bandwidth speed. So basically, ether channel is again a layer 2 solution which will help you to aggregate. When I say aggregate, it means it will help you to bundle multiple layer 2 links between directly connected devices. What is directly connected? This switch and this switch is directly connected to each other. This is important word, directly connected. And they will form a bundled logical single link. So this logical single link now would be of 20 gig instead of two individual links of 10 gigs. That is the beauty of Ether channel. But if I draw the same topology again, consider you have bundled this together. So this is one link now. This is one link. This is another link. This is also one link. Now, if you consider this triangle of green representation, I'll delete this. If you consider this triangle, still one link will go into STP blocking state, because even if logically this is one link, logically this is one link, and logically if this is one link, still combining these three would have one loop. So to avoid that loop, one link will go into the blocking state. So ether channel is about bundling the links. I don't deny that, but up to certain limits. Now, what are the achievements you will do with the help of ether channels? Redundancy can be achieved. When I say redundancy, it means if your this link goes down, which is a part of a port channel, then second link will be used, and traffic will be seamlessly shifted without even knowing. So if this goes down, second link would be used. If this link goes down, if there are more physical links, everything will be used. Those are active traffic forwarding. When I say active, it means traffic will forward from here to, as well as traffic will forward from here to, at same amount of same point of time. More bandwidth. Earlier you could only use one 10 gig link because this was into STP blocking state, which is now, because it is bundled together, you have 20 gigs to use. So this is where you are able to achieve the better in terms of the bandwidth. And simplified management, whatever changes you do, those you will do on the logical interface as a port channel. Another name to ether channel is a port channel, which you will do. Whatever changes you do, those will eventually get implemented on individual physical links. uh, there are different modes what you can run. Two major modes are known as I'm sorry, two major modes are known as PAGP and LACP. So PAGP is a Cisco proprietary. It means you can only configure it on Cisco switches, and LACP is an open standard. Now, when LACP is the open standard, it means with any vendor you can implement LACP. Now, what are different modes here? These are the protocol types in Ether channel, and within Ether channel, what you have are different modes. Um, this on, auto, and desirable, these two modes belongs to PAGP. Active and LACP, active and passive belongs to LACP. So how does this logic works with respect to configurations? Tomorrow I'm already going to cover it, but I'll show you quickly. Let's say this is my switch number one, this is switch number two, and you are going to build a logical port channel between the two. So, and if you running PAGP, so you have to run same protocol on two devices. If you're running PAGP here, you also have to run PAGP here. You cannot do PAGP on one side and LACP on another side. So what are the two options? Desirable. You configure desirable on switch 1, switch 2, then they will build the port channel without any problem. If you configure desirable on one switch or switch 1 and auto on other side, they will build a port channel. And same thing on vice versa, that if you configure auto on switch 1 and desirable on switch 2, still they will build a port channel. But if you configure auto on both sides, then port channel will not be formed. Same thing is applicable with respect to active and passive. That is for LACP. So if you are configuring LACP on both sides, it will be LACP here and it will be LACP here. Here it will be active. Here it is active. Then both sides will form. Then they will form the port channel. One side is active. The side is passive. They will form the port channel. If both sides are passive, then no port channel. This is how your ether channel would be performing, or how this is how your ether channel would be built. Uh, Between the two devices. Moving, no doubts. Moving to next topic. Now, from here, what I am majorly going to speak about is layer 3, which is whatever technologies you have heard till now, those are layer 2 technologies, be it STP, be it ether channel, access, trunk, all these are your layer 2 technologies, whereas power of 2 and whatever we will go ahead, we will run see different routing protocols and everything, those are layer 3. Now when we see layer 3, you have to keep in mind layer 3 is all about IPv4. Layer 3 is a internet protocol. You can give them as a network layer, internet as a layer, whatever name you want to call it, but it is all about IP now. Now, what is power of 2? Everyone must be aware that computers and our networking devices process everything in binary. Everyone is clear about it, right? Now, first important thing is 1 byte, or another name to that is an octet, which is 1 byte is equal to 8 bits. Now, when these are 8 bits, the bit positions are labeled from left to right. And the leftmost bit is known as most significant bit. And the right bit, which is this bit, is the least significant bit. And bits can only have two values, which is value as a 0 or 1. So how these values have been determined? If we talk, we say power of 2, we say power of binary. It means your every number here is a power of 2. And when I say it is a power of 2, it means it is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, 2 raised to 7. Now, another important thing what you have to keep in mind is the world of computers start from 0, it never starts from 1. That's why the value over here has been picked up as 0. Now, this is a simple plain maths, nothing fancy. What is 2 raised to 0? is a 1, 2 raised to 1 is a 2, 2 raised to 2 is a 4, 2 raised to 3 is a 8. Now, raised to 3 means what? Or raised to 2 means what? 2 multiplied by 2. That is multiplying 2 2 times. In this case, you are multiplying 2 3 times. Here you are multiplying 2 4 times. Here you are multiplying 2 5 times. And if you do it, you will get those outcomes. Here you are multiplying it 6 times. And this is helpful. This is easier to understand whenever we will speak about IPv4 address and octets and how do you see it and all those aspects. So this is again 2 in multiplied by 2 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 4 5. Here it is 6 times. Here it is 7 times. 4 plus 3 7. And if you do this multiplication, the combined output you will find out as decimal value is 128, then 64, then 32, then 16, then 8. So this is how you can convert something from decimal to binary or from binary to decimal. This is how you achieve it. Now, if I talk about IP, uh, Internet Protocol, which is nothing but an IP, is just one protocol that resides at internet layer of TCP/IP suite. When I say internet layer of TCP/IP suite, it means if you remember the TCP/IP protocol stack, which another name to that is a TCP/IP suite. At an internet layer, your internet protocol exists. Now, what is job of IP protocol or internet protocol is a data delivery, and best effort is done for delivering of the packets. Now, till now, I have been speaking about frames. From here, moving ahead, I'll be talking about packets. Uh, Apart from that, it also gives you the hierarchical logical addressing, which is in terms of IPv4 or IPv6, to have a scalable networks. What do I exactly mean by that? That you can define a hierarchy, how many number of users you could have in one building. Now, how every end user would need one IP. So if you are having 500 users, you can plan down how many IPs you want to allocate over there and how you want to plan the things. And that's where rest of the things come in from an understanding perspective. Now, IPv4 and IPv6 are two internal, two protocols which ideally exist. Uh, there used to be another protocols also like Apple Talk or TechNet, but those are already obsolete. These are currently existing and both are being used. Now, if you see, this is how the IPv4 header looks like. This is your IPv4 header, and this is your IPv6 header. And this is how, if you will see, the IPv4 header, which is where we will be focusing now, main thing will be the source address and destination address. This address is nothing but IPv4 address. This is what we are going to talk further and how at Internet Protocol, the different other more different protocols what we have at network layer are helping us to achieve the connectivity part. Now, if I move ahead, your IPv4 addressing is nothing but a 32-bit in length. Now, just now I have told you 1 bit, 8 bit is equal to 1 byte. So 32 bits means 4 bytes. Now, these 4 bytes, into what format it has been divided is this is the format. If you see, this is my octet number 1, octet number 2, octet number 3, octet number 4. It means this is 8 bit, this is another 8 bit, this is another 8 bit, and this is another 8 bit. And if you combine them together, it becomes 32 bits. Now, 8-bit means we already just have seen in the previous slide that IP you can have. Can you imagine if I just do it quickly? I'll divide the 32-bit into 4 octets. So this is my octet number 1. This is my octet number 2, octet number 3, and this is octet number 4. Now every octet can maximum have 8 bits. It means every octet can maximum have 2 raised to 7, 2 raised to 6, 2 raised to 5, 2 raised to 4, 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0. And once this is done, again, you have to bring the same concept here. You have to bring the same concept here and same concept here. And if how much is the 2 raised to 7? If we enable it, 2 raised to 7 means 2 multiplied 7 times. That goes to 128. This goes to 64. This goes to 32. This goes to 16, 8, 4, 2, and 1. And if we try to add it, if we do it, 1 plus 2, 3 plus 4, 7 plus 8, 15 plus 6, 21 plus 2, 23 plus 4, 27 plus 8, 35. So this is 5. 3 goes here. 3 plus 1, 4 plus 6, 10 plus 2, 12 plus 3, 15. So this goes to 15 and 1 goes here. So maximum you can go is 255 dot 255 dot 255 dot 255. This is the maximum range of IP address what you can achieve. And for sure, from where it would start, when if all the bits are off over here, what I told you, these all would have either have a values of ones or zeros. So if all values are 0 over here, then overall it would be 0. And from that perspective, what you can achieve is this range. What if you see on the diagram, if you see on the table, that these are the ranges from 0, which are ideally reserved, so don't be bothered about it, but these are divided into different classes. The class A is ideally allocated to larger networks, class B are allocated for medium-sized networks, and class C are allocated for small networks. This is, very hypothetical. This is not a reality anymore, but probably that's how the initial consideration was done. And if you ask me the range, this is how your range will exist, that from 0 to 1 to 126 is class A, 128 to 191 is class B, 192 to 223 is class C, and 224 to 239 is class D, and 240 to 254 is class E, and 255 is reserve. We don't use class D or class E for um, general purpose. Class D is used for multicast, whereas actual IP addresses which are allocated to end host machines like laptops are from this range, class A, B, or C. Is it clear? Well, moving ahead. Now, these are 3 types, but within these 3 types, we also have to consider there are 2 different classes of networks, which are public addresses and private addresses. Now, what are public IPv4 addresses? Those are addresses which are used to reach to internet. It means some few IPs which are used to connect to the internet are public IPv4 addresses. Private addresses are used internally. They cannot be used to reach to internet, or they cannot even, their information cannot even send to internet. INA, which is Internet Assigned Number Authority, is a organization which is responsible for handing out and managing public addresses. And it is not free. You have to pay for it. So that's why if you are having internet at home or in office, you will see that your machines have a private IP addresses. And then the features what we are using is eventually converting the private IP addresses into public IP addresses. If I show you the beauty, if I try to find out what is IP address of my machine, the IP address of my machine is 192.168.168.101, which is a private range IP address. I will show you what are the ranges. And if I just go on Google and if I just try to search what is my IP, it will show you the public IP. So this is my public IP. If you see 110.227.206.27, this is your public IP range. So if you see over here, this is the private range which is actually present on my machine. And with the help of NAT, this IP is getting converted to the IP we just saw. That's how the communication would work. Now, whatever I've written down here, these are the registries as per the region wise where you can go and ask for IPv4 address schemes. Like if you are in Asia Pacific, you will go to APNIC. Maybe if you are in US, you will go to ARIN. If you are in Europe, you will go to RIPE and CC and so on. Every country, uh, they have allocated dedicated, registries to achieve this. Now, next thing is the private IP address range. These are the private IP address ranges what you have, which is 10.0.0.0 to 10.255.255.255. This is your network prefix. What is /8? We will talk about it in some time. Second is this into class B, 172.16.0.0 to 172.13.31.255.255, and 192.168. This is the range. And if you see this, what IP I'm getting, I'm exactly getting the IP from this range. So I've selected it over here. 192 is common. 168 is common. 0, 0. So it starts from 0 and goes till 255. Starts from 0, goes till 255. So 68 is a part of this third octet over here, which is again 0 to 255. If you combine, if you calculate, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on till 255. So third octet for me, what I have is 68, and fourth octet for me, which is again 0 to 255, which eventually covers 168 or 101. Sorry, my bad. So this is my private IP address range. Moving ahead now, ideally IP address components are broken into two aspects. One is a network and one is a host. Okay, and host is again broken into three more components called as network address, host address, and directed broadcast address. And the first address in the network number is called as network address. The last address in the network number is called as directed broadcast address. But what you have to understand, some aspects that pick up this class C network, what I have picked, for example, 192.1.1.0. Now, ideally, when I say that two components make up class ABC IP address, network and host. So 192.1.1.1 here is my network component. It is representing my network component from the left side. 0 represents host component. And I have not brought up the concept of subnet yet, but this is my network number. Whatever you have in the first address, this is for, let's assume my first address, which is 0. That's why 192.1.1.0 becomes my network address, what I have written over here, this. So if I just try it like this, network address is nothing but this value. Now, whereas if all bits in last octet are set to 1, when I say whereas if all bits in last octet, what is last octet? This is my last octet. My last octet, if I write down here 2 raised to 8, 2 raised to 7 to 2 raised to 0. If I enable it all, which is 128 plus 64 plus 32, 16, 8, 4. The usable IP address, your network address cannot be used and your broadcast address cannot be used. So everything which is all 255 IPs, 0 to 255 minus 2. What is minus 2? One is a network address and one is a broadcast address. This is 0.0 in last octet and this is .255 in last octet. When you reduce these two, this is the usable IP address range what you can allocate to the end users or end host machines. That's why the formula is 2h minus 2, which is h is a host bits. Now imagine that before I even speak about it, let me represent you something which is like this. Consider a class A network. I've told you that it can come in the range of 1, 0 is not being used. So I will not write down that. 1 to 126. Everything is a part of class A. I'll assume something as 126 as a concept. Now it is in my first octet. That's why it is class A. How it is decided? With the help of subnet. How subnet is seen? Consider subnet is a representation which is again in 4 octets, 32-bit number. Octet number 1, octet number 2, octet number 3, and octet number 4. And the representation of this is mapped with IP addressing, which let's assume to be 126 for now. This is my second octet, third octet, and fourth octet. This is how things would go. Now, see this scenario. If your first octet is being used with some number, eventually this represents your network bit, which is from left side. If you see the value or if you see it is MSB, which is most significant bit. And if you have already consumed this 126 over here with respect to subnet, the representation is 255.0.0.0. These are, let's assume, to be the predefined values. So this subnet is a predefined value for class A. Why it is 255? Because you have consumed your first octet. That's why it is 255. You have not consumed your second, third, and fourth octet. That's why the values over here are 0. So this is how mappings are done. For class B, anything comes in the range starting from 129 to 191. Now in this case, you will consume 2 octets into the range, which is first octet will be 129 and doesn't matter what is the second octet. For example, maybe let's say 100 dot x dot x. For this represents your class B network when it is 255.255.0.0. How this value has come to 255? In simple words, again, power of 2, 2 raised to 7 to 2 raised to 0. If you add them, you get a value of 255. And because these are 8 number ones here, because 2 raised to 7 is also 1 and 2 raised to 0 is also 1, and in between there are total of 8 ones. That's why this is also denoted as slash 8 or slash 16. So why slash 16? This 8 numbers plus this 8 numbers combining them becomes slash 16. Same way for this scenario, it would be denoted as slash 8. This is how your IP addresses are ideally being denoted between this is how your subnets are denoted. Now, why the subnets as a concept was introduced or subnet mask? Cleaning this, the problem was with class A and class B, you could use too many host digits. You could use too many IPs within the same range. Class A was dedicated for big networks, as I said. Now, if you want to, allocate 500 devices um, into the single broadcast domain, it would give you a problem at layer 2 of the OSI reference model. Too many broadcasts would go. So what they said, we will break them at one layer above, which is that network layer, and that's why they bought the concept of subnet mask. A subnet mask is again 32 bits long, what we have already seen. Just now pick up this as one example. This is one example that this is 192.168.100.1, 255.255.255.0. So this is your subnet mask. The most important thing what you have to understand with subnet mask is your network bits. What are network bits? The bits which are starting from left. So bits are starting from left, network bits are starting from left, and host bits are starting from right. The restriction is your network bits must be contiguous and host bits must be contiguous. It means in the subnet mask, from left side it should be all ones, and extreme right it should be all zeros. You cannot randomly put it. You cannot say that first I'll write down here all ones, then I'll write down here all zeros, then I will again write down here all ones. No, it will not work. From left side it will be always all ones, and from right side it will be always all zeros. So all zeros would represent the host bits and all ones would represent the network bits. That is a whole concept. Now, if I just pick up one example from the subnet mask perspective, maybe let's say 10.1 dot 192.168.1.0/24. What do I exactly mean in this? What are my network bits? 192.168.1. These are my network bits. These are mapped to the first three octets of the subnet mask. Why 255.255.255? How I have come to this conclusion or this /24? See it this way. This is your subnet mask. This is 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 0, 0, 7, 8. Now, if you enable these bits, it means 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, and so on. If you add them together, you get a value of 255. If you add them together, you get a value of 255. If you add them together, you get a value of 255. Them together, you get a value of 0. This is your subnet mask. Another denotion, another way you can write down this is, if you add these number of ones, these are 8 ones. These are 8 ones. These are 8 ones. Combining these three becomes 24 as a /24 subnet mask. That's how you are representing the subnet mask. VLSM. Now, what exactly was the problem that with VLSM you are class full subnetting? The limitation was you could break a subnet, but the subnet mask ideally was expected to be same. So it ideally helped us in saving the IP addresses. As the name says, it is a variable length subnet mask. It means between the two routers, if you only need two IP addresses, why you would allocate a /26 subnet? Because /26 subnet would have more number of IP addresses which are being going vested. So what you did with the concept of support of VLSM, which they introduced later on, you configured only /30 as a subnet here. Now, when I say /30, see the beauty, or if I'll pick up this as an example, 192.168.1.0/26. If I just want to explain you one example, /26. So first of all, break this /26. Start from left side. First octet have 8 ones. Second octet have 8 ones. Third octet have 8 ones. And last octet have 2 ones. Then only your /26 will come in. This all are all ones. 3, 4, 5, 6, 7, 8. And last two, if you see here, 1 and 2 are ones and all other are zeros. Because the pit position we have seen earlier is a 2 raised to 7. This is 128. And this bit here is a 2 raised to 6, which is 64. So if you add them together, the value goes to 192. So what is the subnet mask in another configuration wise? Or another way you can write down this is 255.255.255.192. Now, how many host bits do you have here? These many are your host bits. 1, 2, 3, 4, 5, 6. 6 host bits. The formula was 2 raised to h minus 2. Host bits are 2 raised to 6 minus 2, which is equal to 2 multiplied by 6 times minus 2. Those many hosts what you could configure, which is 62 host IPs you could configure. 2 raised to 6 is 64. Now, a question is simple. How many IPs do you need if you want to make a communication between two devices? One IP here and one IP here? More than enough? Then why you need 62 IPs? And because this was a limitation what you had when VLSM was not supported, there used to be a lot of wastages of IP addresses. And when VLSM as a feature was introduced, this slash 26 eventually could be configured as slash 30. So on same router, one interface used to be configured with slash 30 and one interface used to be configured with slash 26. This is what we have been able to achieve with the help of VLSM. Now, device communication at internet layer, we know that routers are responsible to do the function of finding a destination, to move a packet from one interface to another interface. But to achieve this, to find out the destination, where to reach, how to go, um, router needs to understand or know all the IPs or prefixes or subnets. And to know these IPs, what we need is a routing protocol. So routing protocol, any kind of routing protocol will help us to advertise the information which is directly connected to us, which is present directly to us, will be sent out to the remote guys. For example, take this topology. Now, if this machine on the left side wants to talk to a server on the right side, and it sends a data to, from here, it sends a data to this guy. If this router don't know where is this guy sitting over here, now simple, we know that if we are talking about network layer, the rule is IP address. So let's assume the IP address here is 10.1.1.10/24 and IP address here is 20.1.1.10/24. This is how you would represent the IPs. You create a packet, you create an IP packet. You have already seen the header in which this will be the source IP, this will be the destination IP. So consider this is my source IP here and my destination IP is 20.1.1.10. When it will land on router, router will go and check the destination IP. When it will check the destination IP, router needs to know how to reach to 20.1.1.10. And for that, it has to receive the information from its directly connected neighbors. And for that, you have to run some routing protocol. Routing protocol is responsible to exchange the information about the prefixes. So if this router is connected to this network 20.1.1.0, it will pass on the information to this guy. It will pass on the information to this guy, to this guy. Then they will pass on the information to all of their routing neighbor. Then this guy will pass on the information. Then this guy will pass on the information. And this is how this router sitting over here will come to know if it wants to go to this destination, what are the potential paths. And if you have multiple potential paths to the destination, then it will select one out of the two as the best. And those are done on the basis of the local routing protocol rules. Everything is logical here. Everything have their own set of rules. And once that is done, once the rules are selected, the best path is selected. In this case, this guy has been considered as the best path, so I'll say this as a number one. I'll say this as a number two, three, four, five. So this guy will put the entry into routing table. Entry on the routing table will say if you want to go to 20.1.1.0/24, you should go to R2. This entry will present. So whenever a packet will come, it will refer the routing table and then it will send the traffic towards R2. So when R2 will receive it, R2 would also have an entry into the routing table. And that entry would say that if you want to go to 20.1.1.0/24, you should go to R3. And so on. Every router will have entry, and that's how the packet will reach to the destination. And then a reply packet will be created and further steps will be done. This is a rule of this is how L3 devices will perform the functions of forwarding the packet. Forwarding the packet at L3 level would happen with the help of IP addresses. Forwarding of frame at layer 2 will happen with the help of MAC addresses. Now, routing table is nothing but a database, what we have seen, where the information about every subnet is stored. And decision is made on from the routing table on where to forward the packet. Now, what are rules which are selected into the routing table to make any route where to forward the data? So consider this is my topology. R1 receives the information about the prefix over here, maybe 30.1.1.0/24. And from R3, so R1 says that if you want to go to 30.1.1.0/24, you should go to R2. And if you want to go to 30.1.1.0/25, now two different prefixes, you should go to R2 because R1 only have one entry present into the table. When R2 receives it, R2 also creates a routing table entry. It says that if you want to go to 30.1.1.0/24, you should go to R3. And if you want to go to again 30.1.1.0/25, you should go to R4. Reason? Two different entries are being seen, one with a /25, one is with a /24. /24/25, just now we have seen what exactly is the concept. Now, when R2 receives it, it matches to our requirement. It needs to communicate somewhere in this IP range. So will it send it towards R4 or will it send it the data towards R3? This is where, in such scenarios, the winner is longest prefix match. Oh, I'm sorry. No, what is the longest prefix match? The prefix which is nearest to /32. The one which is closest to /32 will be the winner. So who is there in this case? This guy is the winner. So the traffic will go towards R4. This is rule number one. If this is the tie, the next concept is administrative distance. What is administrative distance? Every routing protocol have a dedicated values assigned. These are nothing but your administrative distance, which helps to uh, show or helps to select the best path in case of a tie scenario. For example, you must have heard about EIGRP and OSPF. OSPF's administrative distance is 110 and EIGRP's administrative distance is 90. So in such case, when my rule number one is a tie, and if it needs to be selected on the basis of rule number two, the one with the lowest administrative distance will be the winner. That's where EIGRP route will be the winner. Now, if this is also a tie, Then metric is a third point. Now, what exactly is a metric in simple words? Is nothing but the number required to reach the destination. Metric in RIP, it used to be considered as a uh, hopcart. So basically, a numeric value which basically is a decision maker on which path will be chosen. And this numeric value again, the lower metric will be the prefer. These are your routing rules which are being followed everywhere on Cisco devices. Now, what does any routing protocol does? It basically helps you to advertise the information about the subnets which you are directly connected on. Or in simple words, let's say um, you have the information about some certain prefix, you will advertise it to your peer. Your peer will advertise it to its peer, and it will keep going on till your whole L3 networks knows about it. When I say L3 network, it means the network which works on IP layer knows about it. It means all the routers, not the end machines. End machines cannot understand anything at layer 3. The protocol, there are different type of protocols, majorly divided into static routing and dynamic routing. Now, what is static routing is um, you have to manually define the destination prefix and what is going to be the next stop. So, for example, the prefix is sitting behind R3, and you will go for on R1 and you will configure that if you want to go to 30.1.1.0/24, you have to go to R2. So you say that go to R2. Same thing you say on R2 that if you want to go to 30.1.1.0/24, go to R3 and so on. This is the static routing. Versus dynamic routing, you don't have to manually do everything. You just have to run some routing protocol. And with the help of that routing protocol, the information will be propagated. Now, dynamic routing protocol are again divided into, I should have written down here as a three parts. Somehow I miscalculated it. Distance vector, link state, hybrid protocol. Now, every protocol have their own limitations as well as their own good sets. Like distance vector means it is any specific direction based. It picks up the values. It don't give you the idea about the overall network. It only gives you about the best routes. This is the distance vector protocol. Link state protocol is something in which it gives you the idea about the overall network. In both distance vector and link state, distance vector protocol don't support any neighborships or don't build any neighborships. Hybrid protocol or hybrid distance vector protocol is a name which have been defined, which has been derived by combining the feature sets from both. Like hybrid protocol only gives you best routes, but with link state you can build the neighborships. Here with hybrid protocol, you can build the neighborships. And the simplest example to these are distance vector. RIP is a protocol if you have heard about it. Link state OSPF is the protocol. Hybrid distance vector EIGRP is a protocol. If we speak about EIGRP, EIGRP earlier used to be Cisco proprietary, but now it is open standard. It means everyone can implement it. Now, EIGRP routers, whenever you configure EIGRP on a router, what you would do, it would start sending a hello packets to become the neighbor, to form the neighbor. This feature of forming the neighborship is from link state protocol. Um, Incremental updates. What is incremental updates? Whenever you have any changes in the network, then only information will be sent. Earlier with RIP protocol, even if there is no change in the information, still it used to send every data. whatever routing protocol information is there, it used to send it, which has been, which is better with respect to EIGRP or OSPF, it sends only incremental updates. So this reduces the workload on the router. Now, hybrid distance vector is where vector ideally shows you it is a direction versus towards which exit or towards which next stop you should send the data. And distance means how far is the destination from you. Protocol overview, again, EIGRP works at layer 3 of the OSI reference model. Protocol used is IP88. Administrative distance value is 90 and 170, two different values because EIGRP supports two different type of prefixes. One is the internal and one is the external. And when you consider both, internal 90 value is for internal and 170 is for external. Multicast address is 240.224.0.0.10. Now, why multicast is being used? Because imagine if there are two routers and you there is some IP address from the subnet what you have configured and you say network statement in EIGRP and you define it. Let's say this. Now R1 don't know if there is any potential neighbor sitting on other side because it would be also a LAN network would be also present. Now that's where they start sending a hello packets with destination IP address 224.0.0.10. And it is sent on LAN segment as well as on towards R2. Now, when R2 will see it and R2 will be also configured with a network statement, R2 will also send a hello. And when these hellos will collide, when these hellos will meet each other's world, they will start building the neighborship. That's where your hellos are important. Hello, again, there is a typo what I have done over here, my bad. When you create too much of data, this happens. And it should have been EIGRP, not OSPF. Uh, hellos over here, whatever you have built now, you want to maintain the EIGRP neighbor relationship. It should not be broken. It should be stable because when the neighborship is stable, then only routes will get exchanged. That's where you are using the hello and dead timers, which are 5 and 15 seconds. So when I say that, this router will send a hello every 5 seconds to R2 and R2, it will expect to receive some hello from R2 within 15 seconds. If you are not receiving any hello within 15 seconds, the device will be considered, the neighbor will be considered as dead and that neighborship will be broken. MD5 authentication in support of BLSM, just now what we have seen that BLSM, how it is supported and why it is needed. MD5 authentication in terms of whenever you are building the neighborship between the two devices, you want to make sure it is authentic. You want to make sure none of the rogue devices are connected to your device and building the neighborship and understanding whole infrastructure. So that's why you are using this for password perspective. Supports load balancing over equal cost and unequal cost. Now, what is load balancing? Consider this is a topology and this is my LAN segment. R2 advertises. So now you have two different physical networks. And what you are doing is you are building the EIGRP neighborship on link number one and link number two neighbors you have. LAN information will go via neighbor one and neighbor two also. When R1 has to choose the best path, it does its due diligence. And if those due diligence are tie everywhere. Like tie at EIGRP level means let's assume the metric what R1 needs to reach to the LAN segment from EIGRP perspective is 100 on link 1 and 100 on link 2. There is a tie. There is no alternate solution. So what you would do in that case, you will install both of the routes into the routing table. So from R1, if you stand on R1 and if you say that if you want to go to, let's say this network is 20.1.1.0/24, for example, R1's routing table will say, okay, if you want to go to 20.1.1.0/24, you should go to R2 via link 1 and you should go to R2 via link 2. There are two different links. basically two different next hops. So in this case, it will do the load balancing or load sharing of the traffic. This is the meaning of load balancing over equal cost. Why the cost is equal? 100 to you tomorrow. Moving further, for EIGRP routers to become neighbors, there are some information which must be matching in the hello packets. And what are those neighbors? What are those information? Autonomous system number. So your router here is capable to configure an autonomous system like router EIGRP 100. This 100 is a representation of autonomous system number. This should match on both sides, then only they will form the neighborship. K values. K values are nothing but there are five different K values, K1 to K5, which I have covered in tomorrow's CCNP Encore section. Common subnet, it means the subnet should be common over here. It is not like you are configuring one value over here and configuring another value over here. It will not work. Your authentication passwords should be matching. So if you have configured a password over here as Cisco 123 and configured here is Cisco 1234, it will not work. The password should also match. Now there are some another important terms in EIGRP. What you have, such as neighbor table. What is neighbor table? Uh, the table where you are carrying the information about your all EIGRP neighbors is where you will have the neighbor table. Topology table is a table where you would have information about all the subnets, what you have received via EIGRP. So topology table is a table where you will receive the information via EIGRP. You will select the best path and then you will push it towards routing table. So from topology table, the routes ideally gets pushed towards routing table, which is nothing but if you see this has been written. Successor, feasible successor, advertised distance, feasible distance is covered under CCNP. Purposely, I'm not going to tell you that now. Next routing protocol is OSPF. Now, OSPF again is a link state protocol which is being used to exchange information about subnets. Few advantages with respect to OSPF are again triggered incremental updates. These incremental updates are sent via LSAs. Link state advertisements. It supports VLSM. It has a metric called cost. EHRP has a metric called metric. OSPF has a metric called cost. Uh, how it is calculated, we'll see it tomorrow. The disadvantages with respect to OSPF are that it requires more memory to hold the adjacency information and the routing tables with respect to SPF. Also, because you are running SPF algorithm or another name to that is a Dijkstra's algorithm, the SPF algorithm needs more CPU processing. But today's world, your routers are capable to handle the CPUs or such kind of requirements. Few other aspects about OSPF. Again, this works at layer 3 of the OSI reference model. What protocol used here is a IP89. Administrative distance we have just seen, which is 110. Now, in this case, the multicast address, what it uses is 224.0.0.5 and 6. Hello and dead timers are 5 and 10 and 40 seconds, which varies um, depending on the type of network. Supports VLSM, we have already seen it. MD5 to build the OSPF neighborship, what we are using is a MD5 authentication. Now, terminologies in OSPF, you have few terminologies like consider this as LSDB and LSA. Now, LSDB, consider it like a map to your mall. Now, imagine this is a big mall. It have different floors. and different floors have different shops. Now imagine this is the entry of the mall, and there is one more big map. This is actual mall. This is the map which ideally says that if you want to go to brand X, go to this floor. If you want to go to brand Y, go to this floor. If you want to go to brand Z, you want to go to this floor or this shop. This map is nothing but LSDP. It is a link state database which ideally carries the information about the subnets and to which devices they are connected. For example, maybe I'll now pick up an example of LSDP that it says that if you want to go to 1.1.1.1, which is hosted here on this router, 1.1.1.1, go to R10, for example. So it says that if you want to go to 2.2.2.2, go to R20. R20 is hosted on this here. So this is R20. So the mapping between the prefix information and the destination where they are hosted is done at LSDB. Second is a link state advertisement, which is nothing but whenever there are any changes which happens in OSPF enabled router or OSPF enabled interface, neighboring device will receive a copy of LSA. By that means, this is my router. This is a LAN segment which has been newly introduced for the first time into the OSPF network. So what R1 will do, R1 will send a LSA, which is link state advertisement, to R2, stating that this is about 10.1.1.0, and if you want to go to 10.1.1.0, you should come to me. This has been informed to R2. So what R2 does, R2 do its all due diligence, does all the calculation. It performs the link state protocol operation, which we will see in detail, and then it will pass on this information to R3, stating that if you want to go to 10.1.1.0, you either should go to R1 or should go to R2, depending on scenarios. We will talk about it later. But this is where your second type of uh, terminology, which is LSA, is being seen. And now, what is link state protocol operation? That just now whatever we have seen. In simple words, whenever any link change occurs, that information will be sent by the router to the neighboring router. Neighboring router will receive it, process it, LSDB will be updated, and SPF will be executed, best path will be calculated. Three steps. So what are the three steps? R1 sent an LSA to R2. R2 received it, which is LSA will be processed. LSDB is executed. So step one, LSA processed. Step two, LSDB updated. Step three, SPF is executed. SPF is executed to calculate best path. And then best path is pushed to the routing table. These are the four steps which will be done by any device. Now, what are the OSPF areas? All topologies will not have any problem. Like 4, 5, 6 number of routers is fine, as the number of prefixes or subnets would be lesser. But imagine if you have a topology of 50 odd or 100 odd number of routers. In that case, SPF execution will be very much longer, very much CPU consuming, and it will take a lot of time to find out the best path. The CPU processes would be very intensive, impacting the performance of the device. So what we do, we divide the whole 100 routers, which earlier were part of a one single domain, again, what we have done in L2, into smaller areas. And these smaller areas, smaller parts are nothing but areas. So if I show you this topology, imagine earlier all of these routers were part of one single big area, or these all routers which are now part of smaller parts. Earlier they were chunk of one big area is what you can say. And now they have been broken into multiple smaller device, multiple smaller areas or parts. So what will happen with the help of this? We are reducing, we are reducing our LSA flooding. When I say LSA flooding, it means certain type of LSAs, which we will be again talking into CCNP's lecture. Certain type of LSAs from this guy will go to this guy and this guy. It will go to this guy. It will go to this guy. But as your area changes, that LSA will never cross to this area. So this is how you are reducing the LSA flooding from one area to another area. And if the LSAs are less, your LSDP will be smaller. And if your LSDP will be smaller, CPU consumption would be less and less performance impact. Now, ideally, there are two type of areas. There are more areas also known as stub, but as spatial areas, which I have not written down probably from CCNS perspective, but those are written into CCNP curriculum. Backbone area, the area which is responsible to connect to all other areas in the network. And ideally, area zero is known as a backbone area. So if you check this topology, the this is your area zero, which is nothing but a backbone area. And this area is responsible to connect to area three, area two, as well as area one. So these three areas, which are non-backbone, or these are known as regular areas. And then you have one as a backbone area. So regular areas, whenever they want to talk between different areas, they will have to traverse via area zero. This is a requirement. This is a mandatory requirement what you have. How does ideally OSPF will build a neighborship? To exchange the information about LSDB, the first and foremost thing what you have to understand is uh, they need to build the adjacencies. Unless the adjacency is not built, they will not exchange the information about the prefixes. And to do that, again, OSPF have hellos. EHRP have hellos, OSPF also have the same concept of hellos. These hellos would be sent every 10 seconds, and these are the minimum criterias that needs to be achieved for the routes to for the neighborship or the neighbors to be built. Uh, like they should be part of same IP network slash subnet. Hello and dead interval timer should be same. They should be part of same area. Either they should be normal area or stub area. Authentication should match. MTU should match. These are the mandatory requirements what you have while building up the OSPF neighborships. Now, what stage does OSPF goes through? There are multiple states in which OSPF passes and have the information exchange. First one is down, in which you don't have any OSP of neighborship detected. No potential neighbor is detected. At init state, a router have received a hello packet. Okay, router have received a hello packet from remote guy. Two-way state. So let's say if this is an example, when this guy sent a hello, when R2 received it, R2 says, okay, I am into init state now. When R2 sends the hello, it adds the router ID of R1 into that hello. Why? Because it knows that R1 is a potential neighbor. So when R1 sees this, that I have my router ID, I have my own router ID into R2's packet, I'll go to two-way state. Xstar state, master and slave roles are determined. Now, what is the job of master and slave? Who will control the exchange of LSDB information? One needs to be boss in that. So the one with a higher router ID will be selected as a master. Exchange, the DB packets are sent. These are another type of packets what you have in OSPF, which basically carries the summary of database, not the full information, only the summary. At loading state, LSR. What is LSR? So let's say R1 sends a summary to R2 and R2 feels that XYZ information is not up to date with R2. What it sends? It sends LSR that please give me the information about, let's say 10.1.1.0/24. This is done with the help of LSR message. When R1 receives it, R2 will give a reply back with LSU, which is link state update packet. And once these are exchanged and acknowledged, they will move to fully adjacent neighborship state. This is how your OSPF will build the neighborships. Next topic is access control list. Access control list is a mechanism through which we can filter the incoming and outgoing traffic. When I say filter, it means you can either permit it or you can deny it. Let's say you want to block communication from some XYZ user to the printer because of any XYZ reason. Now you can do it with the help of access list. Access list can be configured on the inbound direction or on the outbound direction. When you configure it, let's assume on the router or on the L3. So access list can be implemented at layer 2 as well as layer 3. Behaviors are different. You configure an access list on the interface. When traffic enters, it will validate that access list and then it will decide whether the traffic is allowed or not. So this is my inbound access list. And this is wherever traffic will go out, it will be my outbound access list. Ideally, access list commands definitely define or should have a permit and denied statement. Permit means that traffic is permitted and deny means the traffic is denied. There are two different type of ACLs. ACL is an access list. One is a standard and one is a extended. Uh, with standard access list, only source IP address can be filtered. Destination IP cannot be filtered. With extended access list, you can filter source based, destination based, protocol based, port number based, everything is done. What is statement ordering? ACL always goes in a sequential manner. When I say sequential, it means let's say this is first line what you have written, second line what you have written, third line, fourth line, fifth line. If it is not matching first line, then only it will go to second. If it is not matching second line, then only it will go to third. If it is not matching third, then it will go to fourth. If it is matching fourth line, it will not go to fifth. Once it is match, it is match. So you have to be very specific about in what order of statements you are configuring the ACL. Implicit deny. Now, at the end of any access list, there is an invisible statement which is default deny. When I say implicit, it means if it is default. It means if you're having five permit statements, five deny statements, and if it is not matching under any of those statements, it will go to 11th invisible statement, which is going to be the deny statement. Now, I told you that uh, you know every user who is connected to internet practically cannot have IPv4 address. We don't have that many IPv4 addresses. Even if you consider all of the subnets, everything 2 raised to 32 and all those aspects, still we are done. Our capacity is already over. Like a user like me who is sitting at home having a normal GeoFiber broadband, I cannot have a public IPv4 address because it doesn't make any sense to me. So what I need a mechanism which will ideally help me to do my address translation. When I say address translation, what do I mean by that? That my source IP address should be translated into a public IP address so that the traffic will reach out to internet and come back. And when it comes back, again, my destination address should be translated and I should again get a original packet and I should receive it. This concept is called as network address translation. It is written under RFC 1613 1631 because these public IPv4 addresses are not free of cost. Another important aspect is you can hide your network addressings. For example, there is some some company whose servers are being accessed from outside. They don't want to, show their addresses what are being used. So what they do is they do NATing for those IP addresses. Now there are multiple type of NATs. What we can consider first is static NAT, in which you are doing one-to-one NATing. Dynamic NAT means you are doing pool of NATing. You have a pool of IP addresses, um, and then you have part, which is if you don't have multiple IP addresses, still you want your multiple devices to connect to internet. How will you do it? That's where PAT is being used. The full form of PAT is port address translation. So what it basically does, instead of converting the IP, it converts the IP for sure, but it also converts the port and it tracks the port details. That's how NAT is being done. Now these terms I'll be explaining you tomorrow because moment you need to have more understanding on NAT, more diagram would be a feasible way to, I can show you. Next concept is DSCP. Basically, DHCP in simplest word is a protocol which will help you to get IP address to your machine automatically. Because imagine if you have some 50, 100 odd number of machines, you cannot go and configure IP address on every single machine. That is not possible. So what you do, you configure a DHCP server, and with the help of DHCP as a protocol, this machine generates a DHCP request. It goes to the server and server allocates you the IP address. And it maintains all the data, lease time, when exactly IP needs to be renewed and everything. We don't have to do anything. All these informations are being carried out with the help of DHCP. Now DHCP have four type of packets called as D, discover, offer, request, and acknowledgement. So even if in interview, if someone asks you what is DORA process, this is a DORA process. D is discover, O is offer, R is request, A is acknowledgement, which is DORA process. Now what happens in discover? The machine ideally sends a discover message that it is willing to find a DHCP server. Why? Because it have no IP address. The machine have literally have no IP address at all initially. So what it does, it sends IP address to 255.255.255.255, which is a broadcast IP address. Now imagine I had told you that at layer 2 you would have a broadcast MAC address. This mapping is done. So 255 is at network layer. At data link layer, automatically all F will be used because this IP represents broadcast at layer 3. So eventually the mapping needs to be done that way. Once it is done, it will go to all LAN segment. Everyone in their own zone will receive it. The DHCP server will receive the packet and it will send you the offer. It is sending you the offer with, what IP address you should use, uh, and other parameters like what default gateway should be used. Apart from that, what is the leash time, for how much time this IP you can use, and all those things. Once this offer is sent by the DHCP server, it the client ideally sends a request stating that whatever IP you have offered to me, I am fine with it. Okay, whatever IP you have offered to me in the offer packet, I am fine with it. That is request packet. And acknowledgement, once DHCP server receives this request, I'm sorry, message, it gives acknowledgement against it. This is your four-way, four type of messages called as DORA process. Now there is another scenario where imagine if your server is not in your common LAN segment, which is basically earlier it was a part of your own broadcast domain, but now it is beyond you. It is somewhere sitting far into some different range. So in that case, what would happen? In such case, a concept of relay agent is used where whenever any discover message is landed on the router, it says that, okay, I have to encapsulate that packet into a unicast. So here it was a broadcast packet because the destination IP address is 255.255.255.255. And here it is uh, encapsulated into a unicast packet with 172.16.2.11. This is where it is a unicast. Helper address has been configured here, and this helper address belongs to the DHCP server. And once this unicast will go to the server, then it will give the offer, and the whole process will be repeated. This is a concept of relay agent. Security terminologies. So imagine this is your enterprise network on the left side where you have a user, servers, which are basically, today's requirement. Now, every user is approved to have access to everything on the network, and every user will have available resources exactly as per your corporate guidelines. Uh, for example, even if this is your ideal situation, still your securities are not up to date. Secure your infrastructures are not 100% secure. What if the user who have access starts, or the coworker starts, accessing something which is restricted or confidential?
এখন
You
ভাই
need
কোথায়? অফিসে
a
না বাইরে?
controlled mechanism. Now, this
ভাই
is one
অফিসে না
example of
বাইরে?
enterprise. Another example of enterprise
হ্যালো?
is you have
এত
connectivity
এত
to
লাভ
internet, you have connectivity to
এত সাউন্ড কিসের ভাই?
subscribers, you have wireless users. It
হ্যালো?
means guest
হ্যালো?
wireless users would have
আপনার
access
ফোনে
to your phones.
আচ্ছা,
Now, in this case,
আপনার ফোনে কথাই শোনা যাচ্ছে না।
you need to have a very
হ্যালো?
secure platform
আচ্ছা ভাই পরে
to
ফোন দিব।
secure network
পরে ফোন দেবো এখন।
for
ঠিক আছে।
prospects.
অনেক সাউন্ড
Now,
আসতেছে।
consider one scenario in this case that this is box what you have built. Now, what are the parameters? If you see what are the terminologies we are using with respect to security, if we really want to explore, what are the options? There is a secured box what you have created in which the content is very safe, what you have assumed it, but it is very hard time for you to go inside and access the content and come back. So what you do, you put a door to it. Now this door can be opened by the person who is allowed to open, or it can be accessed by someone who is not allowed to open. But in this case, your door becomes the vulnerability. It is a vulnerable part to your system, right? Next thing, if someone is trying to access a door, maybe it will try to use a pry bar. This is the pry bar, whatever name you want to give it. So pry bar is nothing but it. tool which will be used or also store. Last but not least is a threat who is this human who is having intention to use this tool to open the door and access the content whatever is written in it. Now there are different type of attacks what we have. I'm not going to go in depth about them, but brief idea about like attacks that spoof addresses, um, DOS or denial of service attacks, reflection and attacks, man in the middle attacks. These are just one of the what do you call it? Uh, Example like spoof is attacker who is picking up some source which doesn't exist, sending a data to the destination, which is your target corporate server, and when a reply is generated by that, it will be sent towards a destination which doesn't even exist. That is the spoofing of address. Now, second, if you see DOS or denial of service, it means attacker is able to deplete the system resources. So, in simple words, this attacker sitting on the image is constantly sending a TCP SIM flooding messages to this guy, depleting his resources, and when it is creating a reply, the reply is going nowhere because this IP even doesn't exist. So too many sessions of TCP have been formed, and the pool of TCP is over here. In that case, uh, the service is being denied to the legitimate users. This is called as denial of service. Now, in third kind of scenario, um, whereas a reflection attack or man in the middle attack, um, the target is sent. So basically, you are attacking, you are picking up an IP address of a source who is alive. If you see he's alive, you are sending a data over here. This guy is creating a reply against it and send it over here. If you constantly do it, you are hampering the performance of this guy. The motive behind of this hacker is not to let this user work. And in this case, this is a reflector. Why? Because it is only acting as a reflection of whatever this guy is doing it. And man in the middle, very simply, you can say that um, this client is trying to access, or this machine is trying to access this IP address, and it is trying to find out an ARP request to this guy. And this guy is saying that I have this IP. So whatever client information is there, this will be sent to this specific machine, which is, how you are attacking, how you are achieving different type of attacks in today's world. And that's where you are implementing different level of securities. These are the general ideas, whatever I have spoken. Now, last but not the least, whenever you're logging into the devices, uh, you need to control who is accessing it, whether the user is allowed to access, who is the user, and what are the things allowed that those are allowed to be done by the users. These are basically the AAA authentication or AAA model, also known as AA or AAA, in which you have three different parameters called as authentication in terms of who is the user, authorization in terms of what is user allowed to do, and accounting in terms of what did the user ideally do. Now, these AAA as a servers are, deployed with two protocols of communication. One is a TACAX and one is a radius. And TACAX is moreover a Cisco proprietary, whereas the radius is, open standard. Um, and your different protocol uses different mechanisms at the TCP layer, at the transport layer, which is TACAX uses TCP port number 49 versus radius uses port number 1812 and 1813 from UDP's perspective. Now, if this is moreover a simplified view on how exactly you would see that if a user is trying to access this switch, when it will try to access the user, the switch will ask that who are you? It's a very simplified view, by the way. The switch will give the user will give its own name. Now, switch don't know. if this is an authentic user and if it is allowed to log in. So what it does, it goes to AAA server and say, is he John Smith? And if he replies, yes, he is John Smith, then only switch will be allowed to connect. This is a very simplified view on how exactly your uh, connectivities would be seen. This covers all our theory part. For sure, everything is not possible to be covered under the webinars. That is the reason I had also kept one lab. So if you guys have any questions, it is open for discussion now. And we will proceed with the lab as our last topic of the day. If no questions, quick 7 minutes break, and then at 16:40 we will start it and try to finish it up in next 30 minutes. Here comes my lab in which we will build some nodes. I'll pick up VPCS machines as my individual and host. Those will talk to everyone, I'll have a switch which will be acting as my L2 switch. I'll have one switch as L3. I'll have a router will help us to connect to internet. So what we are going to do in the lab, VLAN, access trunk port, STP, ether channel. So STP and ether channel is what we want to achieve. And to do that, maybe I'll add one more switch. This is, let's say, my switch 2. And then this will be used for my internet connectivity. We will build it quickly. We will build a ether channel between these two devices. And these two machines will be part of different VLANs. So we will have to create, or we will have to learn the concept of SVI, which we'll be doing tomorrow, but that's fine. Let's power it on. Feel free to ask. No, sir, it is a 1 day webinar. You cannot have access to the lab. This is my VPCS machine. I'm giving the IP address to that as done. What is the command? VPCS. I always tend to forget this. IP address is what I have to probably write down. No. Okay, only IP. Wow. IP 10.1.10 slash 24. Subnet mask is what we define. Now it has worked. VPC 1 is configured. VPC 2 is what I will also configure. So IP is 20.1.1.10. This is also configured. My switch will have, this is L2 switch. And then with presentation part, I don't need it anymore. This is how you would give host name to the switch. I'm just picking any random name. Access switch, interface Ethernet 0 by 2. Before do that, I want to configure the VLAN. Same concept we have learned at the start of the day. So VLAN 10. This image not correct. Okay, this image is not correct, I guess. Change it. Now it should be good. Host name is access switch. Interface, before interface, I'll configure the VLAN. This is how you would create a VLAN. This is how you would name it. Let's say name is data and then VLAN 20, whose name is, let's say, data underscore 2. I'll configure a specific interface under VLAN 10, which is interface Ethernet 0 by 2 facing towards machine 1. And I will say switch port mode access. This is what we have seen types of switch ports. So this is switch port access VLAN 10 and towards Ethernet 0 by 3, which is facing towards VPC2. I'm going to configure it as VLAN 20. Now upstream, I have two links going towards the two switches. And what I want to use in that case is interface Ethernet 0 by 0. Now I want to configure it as a trunk because we want to pass a traffic for two VLANs. So that is switch port trunk encapsulation .1q. This is the trunking encapsulation mode what I have told to you. And then switch port mode is trunk. You have to execute the same command on 0 by 1. So switch port trunk encapsulation .1q and switch port mode is trunk. So this is your access switch. If I go to one switch above, which is my, consider it as a layer 3 switch. Switches can work at layer 2 as well as at layer 3. So let's say this is my core 1. This is the name what I've given to it. Interface gig 0 by 3, which is facing towards downstream L2 switch. I also would need to have VLAN details created. I am creating an SVI. Don't be bothered about SVI as a concept for a time being. Tomorrow I'll be explaining that. Okay. Now, between the two switches, we are going to build a port channel. But first, I'll get my node 6 also ready. Host name is core 02. Interface gig 03, which is facing downstream. And between the two switches, I want to build the ether channel. So that I also should create VLAN, both of the VLANs. What I will do is I will try to form the ether channel. To do that, I have to go under a specific interface, which is gigabit 0 by 1 and 0 by 2. This is a command which ideally is being used to build the ether channel, whatever number you want to give. And if you say the mode is LACP, the mode is active, it means you are configuring the LACP mode. And if you say the mode is desirable, then you are configuring the PAGP mode. So if you see, creating the port channel has come up, but you will also have to do it on other side. So node 6, interface range gig 0 by 1-2. Let's see if my port channel is up. So ether channel summary P means it is ported and my port channel is up without any issues. So I built this three triangle. If this three triangle is built, it means we have spanning tree already kicked in. So let's check out spanning tree for one VLAN. Maybe I will say, first I will just do this. I will say show spanning tree VLAN 10. So for spanning tree VLAN 10, if you see one guy, this is a switch and you have three interfaces going towards 0 by 1, 0 by 0, 0 by 1 and 0 by 2. And this is root, this is designated. And if I go and check on switch number core 1, it is show spanning tree VLAN 10. It is only one port which is 0 by 3. Why we don't have port channel under a part of it? Show ether channel summary. It is ported. What I have to define is a trunk which I did not do earlier. I'll do that now. I'm waiting for the port channel to be bundled. It is bundled. And if I do show spanning tree now, okay, it is also part of that. Good. This is a root bridge. The concept what I had told you, out of the three switches, the one with the lowest MAC address will be the winner. So if this is a yeah, moving ahead. And it should get blocked somewhere. So if I check here, if it is C, Ethernet 0 by 1 has gone into the block state. So that this is how we have avoided the potential loop between these three devices, which is this switch, and this L2 switch. This is my L2 domain. From here to here, it is L2. Now upstream towards from this switch, upstream, I will form the IP addressing and I will configure the OSPF on that. So let's say gigabit 0 by 0. Some IP addressing I'm using, let's say 155.1.100.2. This is how you configure the subnet mask. And I will also go on the CSR device who is connected to our internet. Host name is IS internet router for us. Interface is gig 3, which is coming to connected to switch 155.1.100.1. And if I try to ping to 155.1.100.2, the communication is through. Now we will build the neighborship between switch and the CSR device. That will be OSPF neighborship. To define that, router OSPF1 network area 0. This is how you define the default build. So I am telling the CSR device that you go and get the IP address from DHCP, whoever is a DHCP server. I have got IP address. This is the IP address. And I'm building. My OSPF neighborship is also built. We are good. Last thing what we are left with is enable the NAT on the internet device. So what I will say, interface gigabit 3, IP NAT inside, interface gigabit 1, IP NAT outside. This is how you would configure the access list to match under or map under the NAT statements. Permit statement ideally says what is permitted. So I'm allowing everyone to access internet. I will say IP NAT inside source list 1 interface gig 1 overload. This concept is nothing but pat what we are implementing. And if I maybe go on my core switch now, if I try to ping to 8.8.8.8, my ping is working now. This ping is ideally going to internet. And this is how you will see the NAT translations being happening. If you see, this NAT is happening. This is how you ideally build the topology. This is very fast. I just wanted to give you a gist on how ideally the things would look like, but this is how you would end-to-end communicate between the devices. So what have we implemented here? STP, VLAN, access, trunk. Here we have Ether channel. Here we have OSPF routing protocol. Here we have NAT with ACL. This covers our today's day. Any doubts? What do you want me to check in NAT config? IPNAT outside is the interface which is on gigabit 1, which is facing towards internet. Inside is where the packet will hit. And this is my pat config. What I have done, I'm telling that whoever is coming to you on gigabit 1, whatever IP is there, you use that and send the traffic out. So if I just do show IP NAT translation, it would be gone now as expected. These are dynamic entries. And if you see now, the entries are created. And in pat, as I said to you, that this is the source IP with which packet was originated. The source IP got converted with this, and destination IP is as it is. Your source port is also being tracked. That is the whole scenario with respect to NAT. Sorry, PAT. Any other doubts? If no doubts, then probably we can conclude. To install this lab in my PC. Sir, to explain this at it will take a lot of time, but what you have to do is you have to install a device, you have to install a software called Oracle VirtualBox. Oracle Virtual, in that you will have to import a OVA file of EVNG, and then you will have to add the images into EVNG. There are step-by-step documents given on Google on installation of EVNG. I can even paste that. This is the website you can on which you can find out all the details. I pasted it already on the chat. Thank you and bye bye.